And for the people at home, we are recording. So yeah, you should be able to do a measurement. I very much agree with that. But can you measure an electric field? Do you have something like an electric field meter?
You measure its effect through the acceleration of the bodies.
Yes, exactly. I mean, what you can measure is ultimately, I think, the only things you really can measure is displacement and an amount of time or something like that. And maybe some other ones, but in our particular case, I think how much something has moved in a certain amount of time, that is something you can actually measure, right? You just take a tape measure or something like that and just see the thing go. An electric field, I don't have a tape measure for an electric field. I mean, I have a machine maybe that can measure an electric field. What the machine does is ultimately measure something moving and then decides that there must have been this electric field there. Right? An electric field ultimately is buried within the Coulomb law, at which when you multiply it with the charge, then gives you a force, and even a force you cannot measure because the force first has to present itself in an acceleration. So what in this long series of observables is the one, from what point on do you call it a real thing? Because if we're going to say this, well, you have an electric field, that gives you a force, and that gives you an acceleration, and that gives you a displacement in space. And you say, well, this you can actually measure. Acceleration, sort of, this becomes more, the only way that you can measure force is by seeing something move. And the only way that you can get the electric field is by having seen something move on the electricity because of the charges. So why is it that from this point on or so we call it real, this is not so real, or this is real? Why don't we say this? Why isn't this part of that same chain? It's a sincere question. At what point do we say something is a real thing and when isn't it? Well, this is not a real thing. Oh, but this is. Yeah, somebody who's very much in favor of force will say, no, this is the real thing, and this is the thing you get, but this is the thing that leads you to the force. Where's the crossing point? It's a serious question. Now, my view on these things is, I think ultimately one of the very few things you can measure is displacements, and then the rest is just mathematical inference.
Okay.
And if that is my personal view of seeing things, then I don't see any less realness in this thing than in that thing. It's just a series of inferences where only the very last step is something measurable, right? So,
I have a question on this. Like,
okay.
what about Occam's razor?
Yes.
So, like, the variable that is able to explain things in the most compressed way is the correct one.
Yeah, but how does it apply here? I know Occam's razor, but where?
Because we know that with the potential we are reducing the amount of variables in our game by describing the same thing.
Yes. Okay, so that means this is actually more real than this one.
No, it's not one thing. It's just an hypothesis. Like,
yeah,
if
sure.
you apply, what about Occam's razor?
Yes.
Because
well, Occam's razor indeed says Occam's razor is sometimes misquoted or misused or not used in the right way. Occam's razor says indeed that if you have something that needs explaining, then the theory or your hypothesis that needs the least amount of assumptions is the correct one.
Yeah.
Yes, or it's likely to be the correct one. True. Well, in that sense, this actually needs less assumptions because this is only 3 numbers. Well, this is also 3 numbers,
exactly.
but magnetic field, yes.
But the electromagnetic theory can be explained with less equations if you use potentials instead of fields.
Yeah, I agree, but I wonder if that is in the case of Occam's razor because you have less numbers. I agree with that, but the numbers still are the same physical effect. Both of these explain the same physics. So Occam's razor is about having added new physics or new hypotheses about nature itself. This is the way that what you're talking about is you have less numbers to describe nature, which is not the same as saying I've added new nature in it.
They're exactly the same hypothesis. So like the Occam's razor, you just like cut down the ones that are more complicated and with more steps. But in this case, actually, they're exactly the same. They just very similar. So
I'm also thinking about my yoga teacher back in the day, who would say if you're going to start something new, then you should pray to the elephant god Ganesha. Okay, all good and dandy. Because Ganesha will make sure that things will work out. So then somebody asked, well, but sometimes things don't work out. And she said, yoga teacher, she said, yes, but that's because sometimes Ganesha makes things not work out because there's something for you to learn. And my scientific mind then goes, okay, so whatever the outcome is, whether it works or not, in both cases you can attribute it to Ganesha. Ganesha, which to me makes it indistinguishable from Ganesha not being there, because no Ganesha would also mean it either works or it doesn't, right? That to me is Occam's razor, that you say, well, of the two possibilities, one of them has to invoke a thingy, and one of them does not, then I tend to go with the thing that does not require the thingy. By the way, that's not a statement about either the existence or non-existence of Ganeshas or whatever. The Occam's razor doesn't say, and therefore this is true. It just says that you have to be careful that you don't put extra stuff in that might not need to be put in. But anyway, all of this, I don't think Occam's razor applies, because all of this is really the same physics. We haven't put any Ganeshas in here. This has as much Ganesha as this one does. It's a mathematical restatement. It's not a new physics that you put in. Now, anyway, this is not liberal arts and sciences introduction to whatever the course is called in the core. But there is a real question at heart here. Again, going back to the one-line synopsis of electromagnetic fields, we rewrote it in potentials, and the potentials don't mean anything. Now, my claim is that yes, they mean just as much as these ones. It's just mathematically more convenient. Yes. And I honestly don't see any difference between stating this one and that one. Not mathematically, but also not physically. There's no other physics in between the two things. Now, what I think you can say though is that in the original description for E and B fields there was at least a certain amount of superfluousness. There were too many of the things. All of them were correct, but you don't need all of them. Yes. So in that sense, I think they're not less real. Let's step away from the word real, but they're just not the most convenient way of writing it. Now, yes, we saw last week that indeed what we end up with is 4 equations that contain all of the Maxwells, and they would look like this. That one. You might notice that I'm now putting in dynamics, not just statics. I wrote a box, a Lambertian instead of just a Laplacian. I hope you see that if you have this one, and it so happens that your A field and phi field are static, then the time derivatives in here just drop out and you get back your original Poisson equation. Right? It's really a generalization of the Poisson equation. So from now on we're only going to use with these. Once you have phi and A solved from this, what do you get? Or how do you get your electromagnetic fields? Just summarizing before I add something new to it. It's important that we have everything on the right place. I found my phi, I found my A, split the equations.
Magnetic field is the curl of A.
Yes.
And the electric field is the
Gradient?
Yeah, the gradient minus gradient of that one. The scale.
Yes. This is not complete.
Minus
Minus, exactly. This part, this is true in statics. But last week we were discussing that if you go to dynamics, so you have Lambertian instead of Lambertian instead of Laplacian, then this is the way to go. I left the piece open here because we also found last week not only can you do this to begin with mathematically, we also found what the general solution is to this, and it's nice to have that as an intermediate step. If you want to know the potential at one point, the only thing you have to do is integrate your charge density over all volume. Just be mindful that what you have to put in is not the time now, you have to put in the retarded time. And the same thing for scalar potential. And from this we concluded by the intermediate step here, we have literally solved all of electrodynamics. It's all in there. You still have to do the integration, but otherwise everything works out. Now I can add a little bit to it. I don't know if this is mine actually.
It's not mine. So.
It's okay. I have to add a small caveat here that I didn't want to express last week, but the integrals do have to exist, yes? If it so happens that the integral for some reason gives you stupid numbers or impossible numbers, then it doesn't exist. Now, there are actually cases where these things become infinite. If you would do the integral, the outcome would diverge. Then you would say, oh, that probably means that you did something wrong. Actually, then in most cases, yes, you would get an infinite integral. But if you would still put it in here and there, you would still get a finite electric and magnetic field, right? So the phi and A, we already talked about this. You have to get their changes to get the electromagnetic field. Now, even something that extends all the way to infinity, is infinitely big, might still change over there, right?
Mm.
So don't worry too much if the thing itself becomes infinite. That's not your problem. The problem, if the change becomes some strange number, then you've done something wrong. A real issue would be if, for instance, the outcome for some reason or another is complex, right? Because that means you have to take the curl and some derivatives here, and that means your electric field will be complex. Well, then you really have a problem, because in the series that we had, the electric field, everything to a force makes it complex, makes your acceleration complex. At some point, things become difficult. I'm sure you think about imaginary time now or so.
Yes.
Okay.
Actually, I also did the exercise again for the analysis of big data of last week.
Okay.
And I found that actually Schwarzschild gives you better solutions than Kepler's. Well, it was because...
Oh, that was the chat exercise,
yes.
Right? Yeah, okay. Did you make a mistake when you did it first?
Well, not in the derivation, the formula was correct, but then I plugged it in a calculator and it was wrong.
Oh, yeah, never trust calculators, is what you learn here. So, anyway, this is all just summary of last week. Again, if you go through this integral and you find that for some reason it explodes, that's not the trouble. Right? The question is not whether the thing is infinite, the question is what is its change. It's something that's infinitely big, might still have a finite change. Or in other words, a finite magnetic and electric field. This is all of electrodynamics, but this is relativistic electrodynamics, so I now really have to put in some relativity. That's for today. Now, in order to do that, we have already made sure that one condition is fulfilled. Last week when we started the lecture, I said, well, at least you're going to need 4 thingies, and not in the original Maxwell's equation, 8 equations and 6 thingies, 3 magnetic field components, 3 electric field components. You need just 4, because ultimately relativity will connect 4 thingies to each other, space and time. So that condition is now fulfilled. We really have 4 of them. That's not a promise that you can now make it relativistic. Now, I'm going to step away from electrodynamics for a moment now and just go back to relativity to find out what the actual condition is to make something really relativistic. Just having 4 numbers, that by itself does not make it relativistic, or doesn't even open the possibility to make it relativistic. It is necessary, but it's not sufficient. So I propose what we do now is keep this now for here. We're going to go back to it later. It's nice I've written down. We have a summary here. Let's go to relativity for a bit and really find out what does a theory need in order to be written in a relativistic form. Yes? So forget about this for now. Let's go to relativity. Now, all of you have done relativity, and I think all of you even with me, so that's good. If there is a one-line summary of special relativity alone, please don't make the statement the speed of light has to be the same to all. Yes, that is true. That's how it was found historically. That's not what summarizes relativity.
Things exist in space-time which can be described by a line element.
Yeah, but no. But that is yes. That's things exist in space-time that has to be described by line elements.
Well, I would guess if something has something to do with relativity, then at some point you would get some line elements in.
So you need something like this. We need a d tau squared, something. Yes. The theory has to be rewritten. It has to be able to be rewritten in this way. Well, that's true. But I can write many theories as a d tau squared equals something. The d tau something has to obey a particular rule. Just writing down a series of numbers and call it a line element will not make it relativistic. That's just a definition of line element. We have to put physics in. Now, where does the physics come in once you have a d tau squared expression?
So is the only thing that she's missing just saying that this line element is invariant?
Yes, exactly. This is not physics, that's just a definition of line element. The fact that whatever comes out should be the same for all observers, that is what makes it relativistic.
Isn't line element by definition invariant?
Well, if you define it as such, yes, of course. Yes. This is of what makes it relativity. Now, with the prime example, of course, we've already seen, right? At some point in the second week of special relativity, when we did away with the somewhat too simple quote-unquote derivation of special relativity with mirrors and thought experiments and everything, I threw it all away and I said, well, if we start with this, then we get everything. And the rest of the whole course, we only used this statement. Now, do you remember what should be here?
Is it c d tau squared minus c squared, sorry, c squared dt squared minus dx squared minus this
one?
Yeah.
Yes. That's the one. That had a name. That was the Minkowski line element. Yes. And yeah, there should be C's. Conventionally, they are placed here. The C's at this point, the only meaning that they have is to make sure that whatever you're going to add to each other have the same units. You cannot add durations, dt's, and dx's, distances, because there are seconds and meters. So some conversion has to come in, and the conversion we're going to call c, and then experiment tells us it happens to be the speed of light. Yes, this is how light comes in. Again, I want to stress, relativity is not a theory of light, it's a theory of space and time. It's just experiments that tells you that the conversion number that you need to make the units come out correctly in the invariant line element has the value of light. That is completely not a given. The reason we call it the speed of light is simply because the first thing that we measured that had that velocity happened to be light. If for some reason people had built gravitational wave detectors before they built light detectors, yes, it would have called this, we would have called the speed of gravity. That does not make this thing a gravity theory. If they had done this measurement for the first time on neutrinos, which they have a very small mass, but for all practical purposes, let's say for now that they go with the speed of light, that's what they thought about 20 years ago. Suppose that they had done neutrino measurements first, and from those they had inferred the value for this number. We could have called C the speed of neutrinos. Yes, the name is completely historical. The meaning is completely historical. It's just light that was the first time that this number was measured, and unfortunately that has sort of, been put into history as if the relativity itself is a theory of light. It isn't. It's a theory of space and time. Now, one final philosophical question, and then I'm going to actually quantitatively do something with this. Even if some conversion factor is in there, and even if nature tells us that, or experiment tells us 300,000 kilometers per second, then still there is no guarantee that something in nature moves with that speed, right? It could have been very well be that, yes, there is something that happens at that speed, namely you get all these asymptotes, your Lorentz factors and everything. It's just so that nature doesn't actually make something move with that speed. You can have a world, in principle, theoretically, mathematically, that has this speed of light, or speed of neutrino, speed of gravity number built in, yet nothing in nature actually follows that speed. That's entirely possible. It's like having a highway where there's this little sign that says you're not allowed to go faster than 100 kilometers per hour, and every car on that every car on that road can only go up to 80 kilometers per hour because for some other reason. Yes, that's entirely possible. You can have an upper limit or a special velocity in nature that has a certain number, and nothing in nature actually has that number. So there's really, if you think about it, two deeper questions here. First of all, why is this number 0,000 kilometers per second? That's question number one. The question number two is, why is it that anything in nature actually follows that thing? Now there's a partial answer to the second question, namely, we derive this in special relativity. If you have no mass, you have to follow that velocity, yes? So the second question, why is it that anything in nature follows this velocity, is partially as by saying, well, because there are massless objects in nature. But then you can ask the question, yes, well, why has nature chosen that some numbers or some objects are massless? You can build a world where massless particles do not exist. Then you would still have this line element, including all the strange effects like time dilation. It's just nobody gets the maximum amount of time dilation because nobody actually hits that number. That is entirely possible. So all of this is just to say something about the C is not the speed of light, and there are some deep philosophical questions involved still. Now, this thing, the line element, and most importantly its invariance, is what got us all of relativity. Everything we got from relativity we got from here. We got, if you remember, time dilation, Lorentz contraction, the full Lorentz transforms. We got mechanics, we got E is gamma mc squared, we got the definitions for momenta, everything came from here. This really summarizes all of special relativity. Well, actually this part, the invariance part, in that combination. Okay? Now, I'm going to introduce some new concepts. They're not new physics concepts, but some new mathematical concepts that we're going to meet later on in electrodynamics. First of all, we're going to start, this is just definition, with the definition of something that is called a Bohr vector. I'm sure in other courses you might have come across the term. I use it every now and then. Certainly in my own personal work I use it all the time. Any idea what a Bohr vector is, definition-wise?
A vector that transforms in a particular way.
Correct. Yes. Now you might be tempted to think, well, any four numbers that you put in a little column and you put two brackets around is a vector of four numbers, so it's a Bohr vector. No. A Bohr vector comes with a mathematical property. It has to transform in a certain way. And a good way to introduce this is to first look at three vectors, normal vectors from non-relativity, from Newtonian physics, for instance. A three vector would be, for instance, let's take here the corner as the center of our coordinate system. A three vector would be any of your position. Yes, because I need three numbers to describe where you are. I might even need two numbers because you're sort of at the same height everywhere, but in principle you could be floating around, and I need three numbers to say where you are, right? Well, let's take your guys' noses because there is some variation there, okay? If I want to know where your nose is, I need to have an X, a Y, and a height, and a Z. Now, if I'm going to look at how far, but let's take any two of you's noses are away from each other, yes? Then what I need to know is, in that coordinate system, where your nose x, y, z is, your nose x, y, z, has to subtract those x's, y's, and z's and use Pythagoras theorem. Then I get a number, that's the distance between you guys' noses, yes? Now, suppose that I'm going to go to another coordinate system, not a moving one, I'm standing still again, it's just I shifted my 0 point. And now I'm going to do the same exercise, then your x, y, z nose coordinates are slightly different now. Certainly they have moved in x, yes? Your nose is still at the same place, by the way. It's just that how I start counting them from what point on is what has changed. His numbers for his nose have changed. In fact, let's make it more explicit. Okay, so let's also change the z number for your both noses. Or I'm not going to stand on my head because that will be parity information. You can even do that. If I stand on my head, then all your previous z's will be minus z's from now on, yes? But in any coordinate system that I choose, your x, y, z will be different, your x, y, z will be different, but the distance, Pythagoras theorem, would still give me the same number. Obviously, you might almost add, because you say, well, how far you are away from each other has very little to do from what point I do the measurement, right? General relativity people, that will not be true anymore in period 5, but here it is. So, what I'm saying here is that there's something about your nose positions and your nose positions and anyone's nose positions that does not care about where I do the measurement. It doesn't even care whether I move, I turn. I should not keep on moving because then relativity comes into play, but if I have turned a little bit and my x-axis has turned a little bit to a y-axis, numbers have changed. Your x number for your nose has slightly turned into a y number. And if I make it like something like this, I tilt backwards and now all of a sudden my x is now pointing upwards. Again, your z number for your nose has changed and yours as well. Still, the distance between your guys' noses will still be the same. Now, anything in nature, those three numbers, that does not care about the observers tilting or moving, not moving itself, but translation of 0 point of the coordinate system is called a three vector. Yes? It's not just a bunch of three numbers, it's a bunch of three numbers that has a property that whatever distance I calculate using those three numbers does not care about the observer's position or tilt or rotation. That's called a three vector. And again, I should almost add, well, that's obvious because distances should not care about how I rotate my coordinate system or where I stand. So it's so obvious to some people that they don't even worry about that might be the case. That's a three vector. Now, can we write down the defining mathematical property of a 3 vector, given what we now just discussed? If I want to know whether 3 numbers, x, y, z, whether 3 numbers put into a column, whether that is a 3 vector, what should I do? How should I check?
Wouldn't you have to have another set of numbers to compare them with?
Yeah, that's true.
Yeah.
Or if you will, which is the same statement, a 0 point coordinate system, right? Because I don't need to know your nose numbers or your nose numbers. I could have chosen the nose numbers in this center, right?
Mm-hmm.
So yes, that's okay, correct. We need a 0 point. I give you a 0 point. How can I check whether x, y, z together make a 3 vector?
The square root of
Rotations.
No,
Sorry.
the
Go on. Well, you can try and transform this vector with rotations and stuff like that, and
Yes.
see if the
Yeah, you could do that. So if you write it as vector, and now I mean a vector in the linear algebra sense, and then you put a matrix in front, and you make sure that the matrix, as you know, what the matrix does is take a vector, turn it into another vector, right? Yes? Now there is a matrix that says how much I have rotated. You might even know what it is actually, a rotation vector. Let's make life a little bit easier, and let's pretend that all your noses are the same height. So for brevity's sake, for my notation, I'm going to start with 2 vectors now. 3 vectors is the same thing, it's just this is easier to write for. Okay, so your nose. Okay. This is y, and this is x. Your nose is at 0x for me in this coordinate system, and it is at y is 1.5 meters or something like that, yes? Now I'm going to rotate. Note where my x-axis is going. Slightly different. I now rotate this fully. How much x does his nose have now in my coordinate system?
Minus y? Is that
Y minus y?
because it's reflected on your y-axis that moved? I'm confused.
Okay, here's my x-axis.
Mhm.
Here's my y-axis. Okay, 90 degrees.
So now x is 0.
Now x is 0, rotate, rotate, rotate.
So now y is 0.
Yes, because this is y-axis, you're now my y0, and now x, what is, if this is originally, y was 1.5 meters, what is it now?
Just 0.5.
Okay, now if it's good, correct, if it's some intermediate angle, I took 90 degrees as a starting example, what would it be? It's trigonometry. High school trigonometry.
1.5 times the cosine.
Correct.
No.
The amount of angle that I moved,
Mhm.
and this one is that one. And then these are zeros. Yes. So that's quite nice. So that means that if I have rotated by this angle, then my new vector, and I'm just applying linear algebra now, would be cosine theta x and y would be something like this, right? Which is correct. Because if I now take my example of just a second ago and take my 90 degrees, then in my new coordinate system, this guy has turned into 0, this guy has turned into the 1.5. That's exactly what we need. The 1.5 would be a number in front, the amount of original distance. So there you go. So yes, what we now have is, we now know how to rotate in 2-dimensional space. One guy's coordinate system to some other guy's rotated, not rotating, rotated coordinate system. And we can turn this into each other. This is still not saying that the numbers, that the distance actually comes out the same. That I have not proven yet. But we're very close. How can I, let's go back to my, here, how can I prove whether this rotation under any angle has made the distance to your nose the same number, has not changed it? We're almost there.
Take the magnitude.
We take the magnitude. This is my original distance to his nose, right? This guy's magnitude would have been this. Yes. And suppose that number is 1.5 originally. What I now have to prove is if I do the same with the rotated coordinate system, it still gives me 1.5. Is that the case?
Yes.
How do we see this?
By taking the magnitude of
Let's
the
take the
final.
magnitude of this guy.
Yeah.
Yes. Here's a question mark. Are these the same? If this question mark is exclamation point, then we have proved that this is a 2 vector because apparently how I chose to rotate my coordinate system did not affect the distance to his nose. Yes, so I only have to prove that this is the same as that. Then I've proven that this xy combination really is a 2 vector. It doesn't matter how you rotate, you always get the same distance. Now, how do I prove that if this is 1.5, that this is also 1.5? We're so close.
Cos squared plus sine squared is equal to 1.
Correct, yes. That's exactly correct. Cosine squared for any angle plus sine squared for any angle gives you exactly 1. So the cosines and the sines, they drop out. Right? So this is just a motivating example. The point here, of course, is it doesn't quite matter how you rotate things. You can easily prove that the rotation, the amount of rotating theta, does not change the amount of distance. Something that you know just for obvious reasons, just from having lived in this world. That the amount of distance certainly doesn't care about how you rotate it. It will still give you the same number, right? So that's good enough. Now, let's move on. We now have a condition to check whether something is a 2 vector, or if you want to make it 3-dimensional, a 3 vector. Namely, apply Pythagoras theorem to it. If you have a xyz and you do Pythagoras theorem on it and it gives you the same number that you would have gotten if you would have gone to another coordinate system, then that thing, apparently that vector must have been a vector, and being a real vector in the geometrical definition of the word. So in 2 or 3-dimensional space, Pythagoras theorem is the thing that defines whether something is a vector. If the distance does not care about how you place your coordinate system, its origin or its rotation, if a bunch of numbers will give you the same outcome for its Pythagorean theorem, then the thing by definition is what we call a 2 or 3 vector. Okay? Now let's move on to 4-dimensional space, because we know from relativity you have a 4-dimensional space time. Any idea what that is? A 4 vector. Something should not care about coordinate system changes.
You could have a 4 vector with the Minkowski line element.
Yes. You have a Minkowski line element, that's this thing, and all of relativity comes from this guy being invariant. This number should come out the same in all coordinate systems. Be careful here, all inertial systems, right? Now, so we know a 4 vector is any bunch of numbers.
I'm sorry, Mendicott, you said that we need a 4 vector that should not care about. Didn't really get the rest of that sentence.
Maybe I write this out first.
The Minkowski line element should be always constant unless with
Be
a
careful,
specific
invariant, not
invariant
Okay,
with a
I was
specific
asking a question
transformation.
before that.
But I don't know
Before
what
that, you
transformation.
wake up.
Yes. Does this help? Any 4 numbers whose Minkowski line element is invariant? It's very abstract, but it really is just another way of saying this, yes? That you have 4 numbers. In this case would be duration dt and distance dx, dy, dz. And a particular combination, this combination, is the same for all observers. If any 4 numbers obey that property, then by definition those 4 numbers grouped together in a column is called a 4 vector. Yes?
And to generalize, you can drop Minkowski.
If you want to go to general relativity, yes, you can drop the Minkowski part. Agreed, yes. For the people who don't want to go to general relativity just yet, leave the Minkowski in. Okay? But yes, in general relativity, if you want to build it up in this way, you can drop the Minkowski and you're looking for any set of combinations that have the same outcome for any coordinate system, even if it's not an inertial system, that's correct. But for us, we're in Minkowski's phase now. Julia's doing this, of course, right? With her magnetic fields around
Schwarzschild.
yes, around the Schwarzschild. Because she's saying that those 4 numbers that create the magnetic field should not just obey the Minkowski line element invariance, it should obey the Schwarzschild. Yeah, that's how she gets her curved magnetic fields. It's a bachelor student from UvA that's working on something related. So this by definition is just a 4 vector. So I can immediately write down an example of a 4 vector for you. Namely, dt, dx, dy, dz, those four numbers, well, they obey this thing, yes, because that's our starting point of relativity. So these four are actually a four vector in the real mathematical definition of the word. So this, if you will, is what I'm going to call a prime example.
Do you need to put minus in front of dt or the other three?
No. I understand the minus thing because there's some minus over there, and that's a notational thing that I will introduce in a moment. They're defined without the minus. So here's an example of a four vector. But in relativity, we actually saw some other four vectors, although I never named them as such.
Momentum.
Momentum, yeah. I mean, one of the ways that we got the relationship between energy and momentum was to take this line element, divided by m, if you recall, or excuse me, multiplied with m squared divided by d tau squared, and then we found that E squared, that was this thing, minus P squared is also invariant. Right? You might remember this. If you take this guy, you multiply all sides with m squared and you divide it by d tau squared. Well, multiplying with m will not change the invariance. Divided by d tau squared will also not change the invariance because d tau itself is invariant. So if you multiply this with m squared divided by d tau squared, you still have a series of numbers added together in a particular way, and it would still be invariant. So in other words, this energy momentum relationship also obeys the property of a four vector. So energy and momentum in three directions is also a four vector. I have to be careful because it's E over C if you keep the C's in. So here's another example of a four vector. Now there's many more four vectors in relativity. And you might already see one lurking in the distance. Because what we now have is you need four numbers, and if they have this particular property, then the whole thing combined is a four vector, and if you have four vectors, that means you can do relativity with it. Now I'm going back to our summary. Do we have four numbers? We do. Now suppose that we can prove that those four numbers actually have the property of a four vector. That means then we can really make relativity out of this. So that's our big goal for today. Show that the scalar and vector potential grouped together in a column with brackets around them are not just four numbers with brackets around them. No, they really have the definition of a four vector. If so, we have relativity. That's it. Now, we need a criterion. What we now have is that if we already know that if you have four numbers and they obey this, then it's a four vector. That's the definition. But and in this case, we know that it obeys this because that's the starting point of relativity. Of these, we already know it because we were there when we actually derived these numbers from these numbers. Yes, but suppose I give you any random four numbers and you have not seen where I got them from, and then I ask you to prove that this is the case. We need a criterion to do this. If you were not there to see it be derived, how would you know of any four numbers whether they actually have this property?
We used rotations in the other case.
Yes.
Should we use the Lorentz transforms?
Absolutely. Going back to relativity once more. Now you see relativity is a prerequisite, yes? Going back to relativity once more. How did we get the Lorentz transforms when we had this as a starting point? There was an exercise in week 2, last year and this year. We got the Lorentz transforms by demanding any relationship between dt and dx and dy and dz such that this is invariant. The Lorentz transforms were found under the assumption that this should be invariant. That's how we got the Lorentz transforms. If you don't recall this in full detail, don't worry about it, but please remember the narrative. The Lorentz transforms were not forced upon you by me, they were forced upon you by this requirement here. Once you want this to be invariant, then we found that space and time should be related in a very particular way. So how can we check whether four numbers are together make a four vector, that they obey the invariance property? Check whether they obey Lorentz transforms. If that is the case, then you're good. That's very similar to the three-vector situation that we had here. Going back to normal space, no time, just space. If I wanted to know whether a distance is invariant, the only thing I have to check is whether they obey Pythagorean's theorem. Yes? Okay, that was our criterion there. Here, our criterion is check whether the four numbers that are given to you, whether they obey the Lorentz transforms. If they do, then by definition, or not by definition, then by inference, then you know that those four numbers are indeed a four-vector. So, this is a definition. Let's turn it into a criterion. I'm going to write it out in full. The criterion is this. If A, B, C, and D, any random four numbers, yes? If you go to another coordinate system, the numbers will change. But if the new numbers are related to the old numbers by Lorentz transform, then it is a four-vector. So if brup changed into brup, as follows, and as follows is going to be the Lorentz transform. Do you remember what it is? So A prime is
Gamma bracket old A minus
or
plus, and then so this is either V times time
yeah,
or V over C squared.
Sure. C squared. Yeah. Unfortunately, this is also C. Oh, you shouldn't do that. Here. Should. Okay. Okay. Make it still be.
Or the che.
Yeah, I have no idea. You know, Lisa has been telling me different ch's and sh's, and they all sound the same to me.
Yeah. So if this is time, then that
Yeah,
was
wait,
like the
it's
x
not
part.
done yet. We're missing something.
We are missing B, ch, and d.
Well, it
Just
depends.
me?
Yes. Well, it depends on what direction you're doing the Lorentz transform, right? Lorentz transform means you go to some other guy's coordinate system, you're moving along some direction. If it is the x direction, then it will have to be here. If you're moving in the ch direction, then it would have been a ch. Now, we did this many times. What we had originally was that for Lorentz transforms this was then typically dt primed. That was the old dt plus or minus v over c squared, where v is the direction of motion, times the b, the dx. And in my more general example, the dx was b. So let's be very clear here. This v is the relative velocity between the two inertial systems, right? Now, it has to be in the same direction as the b1 here. So let's put a little b here. It does not mean the velocity of b or something like that. It means along this direction, the b direction. Yes?
And if you want to generalize it so that it can move in all directions.
Well, let's say that you want to move in ch direction. Yes? So
in ch, b, and d at the same time.
let's do not a mixture. Let's do one direction first. Yes.
Well, then it's okay. Then you just replace b by ch.
Correct. Yes. If I want to know how these four numbers change, if I start moving not in b direction but in ch direction, then this becomes ch, and I have to put the velocity of the two inertial systems in ch direction there. Yes. Now, this directionality in relativity we hardly ever saw, because we were also always moving in coordinate systems that were moving in x direction with respect to each other. We even made a point of this. You can also move in another direction, because you have the freedom to rotate your coordinate axis anyway, you might as well also always put them in the x direction. This is why generally we didn't care too much about directionality. Now I'm going to make it more general now. I'm going to leave it such that you can now move in any direction. You just have to appropriately choose the b's and the ch's and in the right place. Okay? Now your question is, but what if you, right, this is a direction, this is ch direction, and you move in some intermediate direction. The first one I would say, why would you do it? Just rotate your axis first.
Oh, but if your velocity is, for example, changing so that you
Okay, if you have something that happens to move in a very crappy way, right? Jaco didn't really calibrate his particle accelerator, the thing moves in all directions or something like that, yes, then maybe there's a point in making your coordinate system slightly different. Then you can actually do the following. that you have your 4 vector, which now is not along a good direction. First rotate it using the rotation axis in a way where it does, and then use a Lorentz transform in front to do the Lorentz transformation in the direction that is easier. So if something is moving in this direction but my coordinate system is like this, I first rotate, then I do the Lorentz transform, and then I just rotate back.
Yeah, but that's okay. But what if, for example, particle moves in like this, and then it
unfortunately, then there's
leaves
nothing you can do because that's a property of the particle. It's not a property of you. What you can, in principle, do is choose a coordinate system that rotates along with it. So in that coordinate system, it will always move along the x direction. But then it's not Lorentz transform anymore because then you are forcing yourself to go to an accelerating coordinate system, and you cannot use special relativity. So if that is the case, if the Jakkos of this world calibrate their particle accelerate such as the particle jumps all the way up and down.
But you can still be in an inertial system, and then you can still do special relativity.
No. How would you make an inertial system if you have to go to a system that itself jumps up and down?
Well, you can be in an inertial system, and you can know
Correct.
your numbers there, and then you can calculate.
Yes, but a Lorentz transform or a rotation or whatever might bring you to a non-inertial system, and at the moment that you've done that, you're not allowed to use Lorentz transforms anymore.
So you're saying that this formula for Lorentz transforms they cannot use if an object moves accelerating?
Not if you want to calculate the numbers as seen by that thing moving. Yes. I mean, you're free to use special relativity to calculate numbers in that guy's coordinate system. You cannot transform back. But in principle, yes. Anyway, moving on here. This is the definition of 4 vector. This is the criterion. Oh, we're not done, by the way, because the Lorentz transforms have 2 of them. What is the other one in this case? Let's stick to the example where things move in B direction. Yes. What is the other one?
B plus minus, then V.
Change in time.
Yes, then you would have the change in time here, but the change in time will be the change in A or whatever it is. Yes. So this will be A. Now these are just your plain old Lorentz transforms that we also saw as special relativity. And again, please remember for special relativity, we got these Lorentz transforms by demanding that it gives you an invariant outcome. So if you can make sure that these 4 numbers obey these rules, then you can go to any inertial system and every new combination will still uphold the invariance. So this is the definition, and this is how you can check it. I give you 4 numbers, you go to another inertial system and check whether in the new inertial system the new numbers, the prime numbers, obey these rules expressed in the old numbers. If so, it's a 4 vector.
So how come these Lorentz transforms don't need like time involved now?
That's a good point, because the way that we derived them, they had time in it, yes? It's a very good question, actually. Because what I'm now saying is we derived it for time and space, where A was dt and B was dx. And now I'm replacing our results where A was d time. I say, well, any number could have been there, and not just time. That's a good point. Does anyone know the answer, actually? So let me rephrase the question, because it's an important question. His question is that we derive these laws in case this was time and this was space, and yet I'm now using them for things that might not necessarily be time and space. Why is it that I can use the same criterion?
Does mathematical derivation of Lorentz transform requires physical meaning of the one number to be time?
That is the answer. That's actually where the answer is. The derivation of the Lorentz transforms, yes, I did them where this was time and space, but the mathematics doesn't care whether it was time and space. If I had started with a squared minus d squared minus ch squared minus d squared, and I would done the derivation and demanded its invariance, I would have still gotten the same rules. So the derivation, the mathematical derivation of the Lorentz transforms didn't care about the meaning of dt on dx, so it could have been any meaning.
So this is just like one type of Minkowski line.
Exactly, yes.
However, you do put c's there, so I mean by units you're saying that it's not exactly the same thing.
No, there's a point there. So one maybe prior criterion is that the very least that the 4 numbers have to obey it is that if you take this guy, or sorry, if you take A and you divide it by C, it would have to say it must have the same units as B. Yes, otherwise it will never obey that relationship. Yes, I agree.
Specifically C, as in speed.
Yes.
Okay.
Actually, if I can add something, I found an article, a paper, written in 2015 that derives the Lorentz transform without requiring a constant speed limit, and derives it just from group theory.
Oh yes.
And from really basic assumptions.
I know
of
it's
physics.
called the Lorentz group. Yes, for that reason actually. Correct. Yes. Oh.
Hello.
Michaelis, good morning.
Yes. I'm used to you being a couple minutes late. This is a new one. But it's fine. We have. Is there a coffee left? Good. So it's called coffee.
No, I mean it's used. Like, oh no, I thought it was something.
No, it's dented because I it was in a bag with another 11 copies of it. So before we go into break, that's actually a nice moment for you to get a summary. What have we done now? We have defined what a 4 vector is. 4 numbers, yes, let's put the prior criterion in there as well, okay? 4 numbers that obey the following 2 criteria. One of them is the first number times C should have the same units as the other 3 numbers, okay? Okay, that's fine. I don't care about that one usually because C's are 1 for me. Sorry for that.
What did you say?
Okay.
That A divided by C should be B.
No,
I
A
multiplied by
times
C
C should
squared.
have the same units as
Oh.
B, sh, and B, okay? So, okay. That is certainly a criterion. I sort of skipped over it because the C's are 1 anyway, so I don't care too much about units. I should, but I don't. So that's one. But the real criterion is this. It's a 4 vector at the moment that this combination of your A, B, ch's and D's is invariant. How do you check that? Well, because we already formulated the criterion in special relativity in week 2. This is invariant at the moment that the 4 numbers obey the Lorentz transforms. So in other words, if you have 4 numbers, that if you go to one guy's coordinate system to the other guy's coordinate system, and then his 4 numbers turn into his 4 numbers using the Lorentz transforms, then those 4 numbers together form a 4 vector by definition. Yes? Now please note, I haven't added any physics here. All the physics here was physics that we did in special relativity. I just defined a new name and a criterion to check whether something is deserving of that name. That's the only thing that we did. Now let's have a break. After the break, I'm going to show to you that these 2 together indeed form a 4 vector. That they obey the Lorentz transforms. If that is the case, that's good, because that means this line element can be written down in terms of scalar and vector potentials and be invariant. And we can do special relativity. Yep.
Thank you for the coffee and the
Oh, you're welcome. It's
knowledge.
not just altruism. I actually need lots of that coffee myself today. Is this yours? Or neither of them?
Neither of them. I wasn't drinking them, so
Okay.
you can taste that bit.
Then I probably open 2 of them and sort of.
You can also have that.
Sure. Yes.
By the way, at one point we just said, oh yeah, cosine square plus sine square is 1. So this is true.
Yeah, it's recorded.
Which is not really straightforward because you have x and y.
I thought it started at
You have to be a little bit more careful.
Because that was the last email.
I
and
woke
then
up at 9 and I was like, oh, people are late.
I
I
woke
checked
up
my
at 9 too.
I was here 10 minutes late.
Do this.
What did I lose?
Oh yeah. I wrote down a notation
A lot.
matrix.
A lot.
I was
It's
this whole thing. So the whole
Yeah. Like proving that
transform.
this.
It's
Yeah.
this rotation matrix.
Because this is one like just showing that this
Actually-
the magnitude of this is.
that's my only
So
problem.
let's-
I don't
let's do it now,
get out the
just to be
cosine
sure that
square
we have
and the
everything
sine
correct,
square
okay?
out.
Because
So
that means
I-
this is the real
I was actually
rotation
thinking
matrix.
about that
So
during
that
the
means
thing
if
because
you now go to this,
you can't just take
Then-
it out and say it's 1, right?
You can't?
Well,
No.
how do you do it?
I don't
Ah,
know.
yeah, okay,
Gideon
okay.
just said it.
no, but I'm actually improving on that right now.
Oh, okay.
Yes, the rotation matrix. I had skipped
Yeah, right, it's
the
missing.
sign
Yeah.
the sign parts.
Yeah.
If you put that back in and then you
Then you
do
can
the
solve
length,
it.
then everything
Yeah.
rubs out. Yes.
Thank you.
I was a little bit too quick.
How about,
Why didn't you
so
go in my
I will make a
room?
point of that. in a
I'm
moment.
not. I thought you left already.
I was dead.
This is
Yeah.
wrong. This is good.
Because I thought the guy needs to.
Data.
Oh no.
And you have a minus.
Is this one right? This is
Minus in front of x sign.
let's see, x times this,
You don't
that
want it?
times
No.
that. This is correct. This is
Yeah,
correct.
yeah.
There's this, there's that, and that's that, right? That works.
Mhm.
Okay, now let's see. If this guy's length is the same as x squared plus y squared, square root, then it should be
Mhm.
true. So this guy's length would be x squared cosine, well actually no, it's this, x cosine theta plus y
Remember
sine
relations
theta
for
squared
the other way.
plus minus x
So,
sine
So
theta
like if you want to
plus
get the
y cosine
unsigned
theta squared
because I remember here the problem
x
was that
squared
you just use I remember something else
squared
shouldn't have
plus
been so you
y
can have these
squared
times as
sine
well.
squared plus
Yeah,
2xy cosine sine
Mhm.
plus x squared sine squared plus y squared cos squared minus 2xy cosine
Mm.
sine.
And
These
now
two
it's
are
good.
Now it's good. Okay, yeah. My rotation matrix before was wrong. The argument was correct. It's just my main matrix was wrong.
So how did you get it out?
I just wrote down from memory the wrong rotation matrix. I had zeros here.
Oh.
those are signs.
Okay.
Yes, and it should have been completely obvious. Yes, because if I rotate here, then obviously not just his x is going to change by cosine, his y is changing with the appropriate trigonometric function. Should have been this, but now you can really check whether this is the case. Anyway, so I took the liberty of writing a summary on the left-hand side board, where for comparison's sake, I wrote the definition for 3 vector, any 3 numbers a, b, and c, such that if you go to another rotated coordinate system, not rotating, you get new numbers, prime numbers, but the prime numbers and the old numbers are related in this way. Yes, that the length, right? That was the distance to Mickey's nose before. If the length does not change, if you go to another coordinate system, then by definition those 3 numbers a, b, and c or a, b, and ch are called a 3 vector. Again, it's a little bit overkill to do it in this way for 3 vectors because everybody sort of intuitively understands that this is the case. But you know, sometimes you open up a linear algebra book and they take an example from quote unquote physics, right? They show how matrices work and they take an example and say, well, you have the temperature and then you have the distance and you have the electric field, or so in x direction. And they say we have this vector. Now, to me, using a more strict definition of vector, this is wrong. Yes, there's no way that you can rotate the coordinate system such that the temperature all of a sudden becomes an electric field. Okay. So, of course, no linear algebra book has ever said this. Okay, but just to point out, it's an overkill definition, but you have to be careful. Now, in very much the same way, yes. That's the third one. Aside from the coffee I had at home. If you go to 4 vectors,
100 grams of sugar gave you.
it's fine. I'll go to the gym this weekend.
Right.
But 100 per. I hope not.
No.
Okay, good.
Otherwise, I will sacrifice myself for the group.
It's not good for me. Okay, I just put it here. 4 vector is very much the same definition. It's 4 numbers now. Such that if you go to another, not a rotating system, rotated system, but to another Lorentz, inertial frame. And you know physically what an inertial frame means, right? Please. Help me.
Where Newton's laws don't work.
No, that's an inertial frame. You go from one inertial frame to another inertial frame.
From a non.
Yes.
What's the question?
The question is, I say, well, when you go from one inertial frame to another inertial frame, okay, what does that mean physically? Right, I'm now in an inertial frame, okay? I want to go to some other inertial frame. What do I do to end up in the other inertial frame?
You change your velocity.
I change my velocity.
And that's acceleration.
Sorry, and?
If you change your velocity, that's also acceleration. So for some moment, you're not in an
Sure,
inertial frame.
that's fine. I have to accelerate to get into the other inertial system, but once I reach my cruising velocity, yes, and then I stick to it, then that new coordinate system is a new inertial system, right? So when I say go to one inertial system to the other inertial system, it just means start out in one and start moving with constant velocity with respect to the original one. Then you're still in an inertial system. And you're right, the actual practical step of having to accelerate first and then deaccelerate when I reach my cruising speed, fine. You're right, but
That was like the rocket going somewhere and then turning around.
yes, the turning around point is where you briefly are not in an inertial system anymore. But if once you're there, so you are looking at 4 numbers, 4 observables, you've measured them, you start moving into another coordinate system that's moving with constant velocity with respect to the first. Then you measure the same 4 numbers, you get different numbers, A prime, B prime, C prime, D prime. If they are related in this way, my old numbers and my new numbers, and they're related in this particular way, then those 4 numbers are called a 4 vector. Now how to check? Well, this is true. This is just another way of saying invariance of this particular combination. This is true, as we proved in special relativity, at the moment that the 4 numbers transform using Lorentz transforms. So that's our criterion. Okay? So again, the only thing we've done now is we've just defined a word, 4 vector. And we've given a criterion to do it. Now, again, my big goal here is to show that these two are a 4 vector. They are, but we have to prove it. The way that I'm going to do this has some mathematical steps that are for you to solve in the tutorial. But let me first introduce a final piece of notation. This again, notation. Once we have the notation down, I can do the proof for you, and then we're done for today. Now, notation, this combination, writing this out, takes time. Literally, it takes a while to write that down, yes? So, what people did, like Einstein himself did this, he defined a new notation to make these calculations look a lot shorter. Still the same physics, still the same mathematics, it's just the notation that is different. He did it as follows. For the people who have not seen this before, it's going to look horrible for a while, but hopefully by the end of this lecture you have seen that despite a horrible looking complicated mess, it's actually quite elegant and a good way of writing this. I've introduced new notation. 2 thingies. First of all, I've introduced the x with a little Greek index on top of it. This is shorthand. It means the 4 components of a 4 vector. All 4 of them.
The 4 components of the 4 vector.
Yes. So in my example here on this board, this dx with the mu on top is another way of saying all these 4 numbers. It's just another way of saying this.
Okay.
What does the Greek index tell you? Well, the Greek index, by definition, again, it's all just notation, can have 4 values, 1, 2, 3, and 4. You start counting to 0. 0 means this one. If mu is 1, it's another way of saying, I mean the b. If you say mu is 2, you mean ch, and if you say mu is 3, you mean the other one. It's like Python. You can start counting a 0. You have an array. You say array 3, then it means the 4th number in the array. Yes, that's literally this thing. So that's that. So really, this is just these 4 numbers combined, and depending how you've chosen your mu, you mean one of the 4 numbers. This, by the way, dx mu. This is the Greek. I'm sorry, Michaelis, but as you know, my Greek alphabet is hideous. What I mean is the Greek letter n. Then this is the best I can do. Okay, this is mu. It's my mu. Means exactly the same thing. And then you might say, but yes, but why would you introduce another Greek letter if it really is the same thing as this? Mu 0 means the first means A. Mu 1 means B. Mu 2 means ch. And mu 3 is D. Well, why would you do that? Well, first of all, note that it doesn't matter, yes? It just means which of the 4 numbers are you referring to, and which iterator, which object you use to differentiate between the four numbers, that name has no physical meaning whatsoever. So if you want to call it mu or nu or lambda or kappa or omega, that's completely up to you. Convention in relativity is that if you mean by that index, it's called an index, if you mean by this index one of those four numbers, you write it with a Greek letter, a smaller case Greek letter. The typical numbers that people use are mu and u. This is why I choose them. Other ones you frequently find are alpha and beta. So it really is the same thing. Okay. Going again to my Python example, you have an array, and you take its. You want to have its third element. You can say array square brackets I is 3 or something like that. Doesn't matter if you wrote j is 3 or k is 3. In all cases, Python understands you meant the third one. Very much the same. Now, I also introduced something else. An eta with a mu and a nu, two of these things. This again is shorthand. At this point you might already think this is very much overkill for something very simple, but it will get better in a moment. It's just a little bit of rambling that we have to do first. If you have two of these, then that means, and each of them can have 4 numbers, you have 60 numbers in total, right? So that means if you want to write it down, it's not going to be a column vector anymore. It has to be some matrix shaping with 4 numbers down and 4 numbers in a row. This eta, by definition of eta, is a very particular set of 16 numbers. Here they are. Okay. Most of them are 0.
But there you used minus for the xy parts.
I know this.
What?
There you used minus for the xy parts, and here you used minus for the time parts.
There's a convention issue there. We'll make a decision in a moment. Both of them work.
Yeah.
Okay. So, we have this. Now, just as a check, suppose that I tell you I'm interested in this number. Of the 60 numbers, I want the mu is 1, nu is 3. Which one of the numbers do I mean?
0.
No, that's correct. If you, I know you know why, but if you didn't know why, you might think, well, most of them are zeros, probably one of the zeros, right? I have a, what is it, 4 on 16 chance or so that I have the right one, so 25%. But yeah, it just means take the first row, and you have to start with 0, 0th row, first row. So this one means we're looking here now, and within that, take the third one, and the third, again, you count starting at 0, so 0, 1, 2, 3. So I was talking about this number. Yes. In fact, you can immediately see that the only numbers that are not 0 here is any mu and nu that are the same. Right? Alright. Now, final piece of notation. If you have one of those index thingies with the Greek index down, like this one, and you put one with the Greek index up, it's a shorthand for the following. Again, it's all just notation. Shorthand for the following. One index up and some other place the same index, so one down and the same index up someplace, means, okay, take mu to be 0. If this mu is 0, make that one mu also 0. You get a number. Yes, you pick the numbers from here. Then you do the following, so you get a number. Then you do the following. Then you take mu to be 1. Now you take the number 1 and this guy the number 1. You get another number. Do the same for mu is 2. Take this one to be the number 2, that will be the number 2. You get yet another number. And you go to the last one, take mu to be 3, take this mu to be 3, you get yet another number. You get 4 numbers now. Then add these numbers together. This is so important, this notation, that I'm going to give us a little extra piece on the board here. So, more generally speaking, if I give you a 4 vector, 4 numbers, with an index down, note that I'm not specifying what those 4 numbers are, but I write A as if it is a vector potential, not necessarily, it could be anything. And I have another thingy, B, not magnetic field, whatever. And I have another mu here, yes? Then by definition, just notation, this means A0, B0, plus A1, B1, plus A2, B2, plus A3, B3. That's by definition what that notation means.
So it's like iterate from 0.
Correct. And then
Okay.
add.
Okay.
So I don't think much in terms of Python, but in Python this would be you list a sum or something like that, right?
So then if you just would have the new be like 2, then it would just do 2 and 3.
And sorry, if what?
The new,
Yeah, there's music.
yeah, if that was set to 2 at the beginning, then you would just do A2, B2, A3, B3.
No, no.
Oh.
If this was 2 and this was 2 from the beginning,
Uh-huh.
you don't mean this at all. You literally just means take the second one of A, take the second one of B and multiply with each other.
Okay.
No, it really is this. If the mu's are unspecified,
Uh-huh.
and you find one downstairs and you find one upstairs,
Uh-huh.
then you have to do this trick.
Okay.
And again, there's no mathematics or physics involved, it's just notation.
And if they're specified, then you just do that exact one.
Yes, exactly.
Okay.
So if they're specified, you don't have to do this at all. This definition, this particular combination has a name, it's called a contraction. So from now on, I'm actually going to use that word as a verb. And later I'm going to say, I'm going to contract this thing with that thing. But what it says here is, I've contracted my 4 vector A with 4 vector B, which is shorthand for saying I've done this full operation. Yes. Now, small check thingy, how about this? I have the same A and B, it's just I don't call these indices mu, I call them nu. So I've contracted A and B again, but now with nu as an index.
That doesn't matter.
Everybody agree on that? That's the same thing, right?
I have no idea.
Okay, then it's good to spend a little bit of time on this.
Sorry.
Can somebody explain to Raquel that this is really the same as that?
As long as the indices are the same, then it's the same operation as up top.
Which is that you give a name to it and not really like a meaning to the symbol that you write in the index.
Yeah.
That's correct. I mean, again, contraction. Hey,
Almost took you.
yeah. Contraction just literally means take the 4 numbers that these indices have, add them together. Now, the 4 numbers that these indices that A and B have, those are the same, no matter how you call the labeling, right? So adding them together will give you exactly the same thing. Here's an example from mathematics where you can see this much more clearly. Suppose that I have the following. I have x squared dx from 1 to 2. Let's do this quick exercise. What is the answer? First year calculus. What's the antiderivative of this guy? Yes. And then you have to plug in x is 1 and then x is 3, yes? And subtract it from each other, right? So you get 1/3. This is 2, yes. So you get 2 to the 3 minus 1/3 1 to the 3. Agreed? And some number comes out because this is 4, sorry, this is 8, so this is 8 over 3 if I'm not mistaken,
Yeah.
minus 1/3, this is 7 over 3. Agreed?
Mm-hmm.
Now what does an integral do? It just means, well, take all the x values between 1 and 2 and add everything together. That's what it does. Now so I'm going to do the following exercise. I'm going to take the same thing, but instead of calling the numbering x, I'm going to call them y.
Oh. So that's it.
You get the same thing, right?
But that's literally it.
That's literally it,
Oh.
because the y here just labels the numbers that you encounter along your adding, your addition, and what you call the numbers, the values of numbers are important, not what you call them. This will give you.
Can we leave it out?
I have no idea what's going on here.
You can lock the door if
I
you
think
want.
it's the welcome thing on the. Yeah, that's
People are
also
not
works.
welcome here, okay? You will get the same answer, right? It doesn't matter how you call the numbers, you just care about their values.
Okay.
And that's the same here. It doesn't matter how you call the numbers, the only thing you care about is what their values are. It doesn't matter if you have nu or mu, as long as you change them both, you get the same outcome. Now, it will be different if you change this mu into mu and leave this mu as mu. So you get something like this. Okay, but then you have a different situation, because in this example that means you would have had this, you would get a completely different outcome. So the point here is, this is a contraction, and contractions do not care about labeling. Yes?
But if you actually do that, it's okay because mu and nu are a series of from 0 to 3. No.
If you do this?
Yeah.
Yes, but the notation doesn't apply anymore. This contraction thing.
You don't have a
Yeah,
plus
totally
just
the
in
same.
between.
It has to be the same. It's not just any Greek letter down and any Greek letter up, no, the same one. And again, no physics, no mathematics, notation. Now let's apply that right here, right now, because look, going back to our Minkowski line element, all of this is just to introduce that you could have also written this like this. And now you think, wait a minute, that's a huge amount of overkill to introduce all that crappy new stuff just to write something that consists of only 4 terms. Agreed? The reason is general relativity. Because in general relativity, you will find, if you're going to follow that course, that you have combinations like this that could consist of 16, in some cases 196 of these terms. You don't want to write all of them down. You're happy with a notation like this. So it's a little bit of overkill here. But there's another thing. It's not just economical benefit. It's also that once you've learned how to operate with this, you never have to look at the plus, minuses and everything again. These come with their own sets of rules, that once you have mastered those, you can breeze through calculations without ever having to write all these separate terms out. So it's a little bit of a steep learning curve, but once you have the notation down, it comes with many benefits. Now let's check whether this is true, that this really is that.
So I'm sorry. So then the dx mu and the dx v,
Yes.
those are both just. Why are they different? Why
So this is what that means. Dx mu just means that thing. Oh yes, and you should put the c's in, which I hate.
and dxv also?
Yeah, dx mu, yes. It's just the same thing.
Okay. Cool.
Now, shall we check whether now this thing is this does indeed give you this?
If you multiply by a minus sign.
We're not there yet, but you're right. By the way, this is what we call a double contraction, because you have 2 Greek indices up and down. This one is contracted with that one, and that one is contracted with that one. Now, yeah, I mean, what you have to do is look at the same index up and down. And if you find the same one up and down, then you have to do this trick. So I have 1 mu down, we also have 1 mu up, so that means this trick applies for this and that, but you also have a mu down and mu up, so it also applies to these two. So you can already sort of imagine this will have 16 terms in total, because a contraction gives you 4 terms. But you have 2 times 4 terms. Now be careful, not 2 times 4 terms. For every of the one term of the one contraction, you have 4 of the other one. So that gives you 16 in total. Now, we can be dumb and write down all the 16 terms, or we can be smart. I prefer to do the smart one. So, let me first do a little beginning of the dumb version, yes? The dumb version will be this. Well, let's do the contraction over mu first. So I'm going to leave the mu's as they are, leave them for a later step. So the contraction over mu is what I'm going to do first. Well, by definition means, okay, take mu to be 1, or 0, excuse me. The nu I'm going to leave for now. Then this dx mu should also be 0. That's by definition of contraction. And this dx mu I leave as is. Plus, okay, that's this one. I also have to do mu1. And I'm going to leave u as is. And so here's one contraction. Here's the mu contraction that I wrote out. Okay, 4 terms. 4 terms. But each of these 4 terms still has a remaining contraction, themselves giving 4 terms. So this turns into 4 terms, this one into 4 terms, this one into 4 terms, that one into 4 terms, total 16 terms. That's a lot of writing. That's the dumb version. Let's not do that. Let's be clever. Look at the object here. The new contraction says, well, take nu to be 0, 1, 2, 3. We are, when this guy is this row, right? It's the 0th row. there's 4 terms that you have to add together when you sum over the news. But 3 of them are going to be 0. So you might not want to add these. Okay. So which of the 4 news that you find in this contraction is one that does not give you 0?
0.
The same things.
0, 0,
0, 0.
0.
So if you want, you can write out the 4 terms, get 4 here, and then read off from here what these 4 numbers are. You can, don't do that, takes forever. Be smart, you say, well, if mu is 0, that means I'm in this row. And of those 4 numbers that I have to plug in, the only one that is not 0 itself will be this one.
0, 0, 1, 1, 2,
Correct.
2, 3, 3.
The same applies here, yes? For this one, mu is 1. You are in this row here that has 3 zeros that you don't care about. The only one that you do care about is this 1 here. So that means the only one that you care about is that one. That's mu is 1. So that the only one that is important is the 1, 1 version. The argument applies to all the other terms as well. You get this. Okay. We've now done the double contraction. The notation issue, you see dx3 here, it does not mean dx to the 3rd power. It means the 3rd element of that 4 vector. Now we can read off the numbers. What is eta 0, 0? See your definition. That's -1, right? And what is dx0?
CDT.
This, and now I'm going to put in the numbers. This guy, I can read it from here.
-1.
-1, okay. And dx0, I read off from this guy.
Oh.
That's CDT, but there's 2 of them, so you get C squared dt squared. Hey.
C squared. Oh, ya entendí.
Now, Elitza already saw this appearing at the horizon, and there's a minus sign. I will get to that in a moment. Now, eta 1, 1, that's this guy, that's just 1. And it gets multiplied with dx1, which is dx. So it's really just another way of saying plus dx squared. And then if you continue, it will be dy squared plus dz squared. Now look, that's exactly that, isn't it? Now here's your minus sign. Do you see that this guy gives you all of this? Yes? Except for that minus sign, right?
Mm-hmm.
Okay.
Oh my goodness, this is so beautiful. Thank you so much.
Okay, don't take me, thank Einstein.
Yeah,
He-
just thank you for teaching me.
Oh, I'm happy to do so, yes. I'm just a messenger, I didn't invent it. Einstein actually thought in a half-joking fashion that this contraction, which is also called the Einstein convention, was his most important contribution to science. Not relativity, not photons, not gravity, no, this notation, because it cleans up stuff. Now, why is this so economic and why is this so good? Well, I already mentioned general relativity. In general relativity, this guy, eta, will be replaced by something that is much more complicated that does not have all these zeros. So in principle, you would have to sum over all the 16 numbers because it's ridiculously big. Okay, so what do we have now? We have that our Minkowski line element. From now on, we never write anymore in this way, the complicated way. From now on, the Minkowski line element will be this. I want to stress one more time, it's just notation. It's the exact same thing. It's just notation-wise, this is how we're going to do it from now on. We're going to write the Minkowski line element as a double contraction. Yes?
And this looks very similar to the final thing we're going to.
Yes. Everybody clear on the notation? Double contractions. We can remove this. In the tutorial, we're going to do an exercise. There we go. In fact, let me also erase this. In the tutorial, what you get to prove is the following. If you have a 4-vector, the time and space 4-vector, and you go to a different coordinate system, a different inertial system, it turns into a primed version, right? dt becomes dt primed, dx becomes dx primed, etc. Then you know how these numbers are related, namely by Lorentz transforms. Now, before we wrote it down with actual gammas everywhere, which is correct. We're also going to write this as a contraction. This is your Lorentz transform in new notation, in the double contraction notation. You have a big lambda here.
No.
Hey, hi.
We have lessons here.
That is very strange. What time?
11.
Yeah, 11.
From 1 from 11 to 1.
That is so surprising
think
because I booked until 1:30. I mean, I believe you, but somebody made a mistake, I guess. You don't have to check, I believe you, but it's just...
Maybe it changed.
No, I don't know. We should... Yes. What should we do? How is it now? Because it's now 11? Yeah, you guys want to stay here, but there seems to be a double booking.
Yeah, I think that's a good idea. Ask.
Because I already done the lecture.
Wait, it's wrong? No,
it's like a cliffhanger. Like, what's gonna happen?
Do you want to know what happened?
Yes.
Yeah.
I mean, you have his number, don't you?
You're welcome to join if you
Maybe it's this one.
double contractions, but
It's one.
what I am going to ask you to prove in the tutorial is that your Lorentz transforms, which you know by heart, can also be written as a double contraction, but it's up to you to find what thing comes in the middle. Now,
What is this?
yeah, that's up to you to decide, but it's a block of 16 numbers, right? Because it's double contraction, you go to these 16 numbers, excuse me, it's a block of 16 numbers. It's up to you to decide what those 16 numbers are. I will tell you the name though. This guy is called, well, it's a tensor. Forget about what a tensor is, it comes with its own definition. Just a name for now. It's a tensor which carries the information of a Lorentz transform, so it's called the Lorentz tensor. It's up to you to show what this thing is. In my crappy Greek handwriting, this is the capital L for Lorentz. That's a standard notation.
The triangle?
Yeah, it's sort of a triangle, but it doesn't fully close. That's how I write my capital L's.
There's no need to get that, like, have that line in the end.
It's because you get
It is
like,
enough.
Yeah, you can
do
do
the
the
contraction.
contraction.
You make your life too difficult, Gideon.
Or if you want, you can put 2 lines in the end, but that's...
2 lines.
Can you draw it for us?
Oh,
Or you
You're
can
green.
you explained that.
You
write
know
like
this
that if you
stuff.
want.
Oh yeah, that also works. Okay.
But most of the time you just write like this.
You know, I've always written it like this. You know, that's just me.
Yeah, you've been lied to.
Yeah, I'm lying to you right now, so I just...
We're
And
used to
the
it.
sort of V-looking thing, is that subscript or not V? But,
What's that?
Was it ni?
New.
Ni. And is that ni subscript or is that just?
That's new subscript. So
Okay.
this guy comes with one upscript and one downscript.
And the other one's mu.
This is...
And the other one's nu.
Yes.
Learning letters.
Alright. Now, once you've proven this,
You can prove it.
we're probably going to be kicked out in a moment, so we have to see where to go and everything. Well, we'll see really, yeah. But okay, we can have them. So I guess we'll do the rest of the tutorial in a moment, but let me already guide you through the steps, yes. There's another thing. Yeah, I told you have to get used to the notation, but once you have figured out what the Lorentz tensor looks like, and you should be able to do this because you know what a Lorentz transform is. Then the next exercise I'm going to have you do is prove that this is the case. that this eta that we had before, right? The one and the minus 1, 1, 1, 1 big, the rest 0 matrix. That this Lorentz tensor and this tensor, it's called the Minkowski tensor, together obey this rule. It's something you have to prove for yourself. You want to do this in the tutorial.
See, it's the same thing here then. That's one is the inject alpha data and then you have to move that state.
So basically
So the capital L, that's a 4x4 matrix.
Sorry, which one?
You said the capital L, that's a 4x4 matrix.
Yes.
You just do the contractions with the other ones and the other ones.
So here the second drop end, what is that called?
This one?
No, the big end.
That one?
Yeah,
That's called the Minkowski tensor.
okay.
Right? It's a block of numbers that we need to make the Minkowski line element. So it's called the
And
Minkowski
what's
tensor.
its letter name?
Eta. And this is a standard notation. All books on relativity, general and or special, will have etas when they mean Minkowski tensor.
Okay, so the second Minkowski tensor is setting the alpha and the beta, which the two big L's are going to iterate over.
Yes.
But then the first Minkowski tensor is, I don't,
What is your question? Is this a
Why
question
is
of
there-
notation, mathematics, or physics?
I think everything, but what's the subscript and the script?
You know, let's start with reading the notation. How many terms are this? Even without writing them out, just even without knowing what these things mean. How many terms? Something plus something plus something plus something. How many of those?
Yeah.
Just from the definition of contractions, how many terms?
64.
Why 64?
I think
4
16.
times 4.
Well, let me start with a simple question first. How many contractions are there? Not how many indices, but how many contractions are there? How many times do you have to do this trick? How many combinations of the same up and the same down do you have? Twice, right?
Yeah.
This guy and that guy and that guy and that guy. You have more indices, I agree with that.
Yes.
But the ones that have to follow this rule due to contraction, there's only 2 pairs of those.
Okay, yes.
Each of the pairs gives you 4 terms.
Yes.
So this will give you 16.
Okay.
So already, even if you had no idea what eta and the Lorentz tensor are, you know that these are 16 terms in total. Now nobody wants to write down 16 terms. Yes. This you write down in 1 line.
Are we also going to be looking at the electromagnetic tensor? Yeah, the one that's -1, the one that was on the board before.
What about it?
Are we going to be basing our number picking from that one?
Yes.
Okay. Okay, and then the second question is what are the subscripts? So the mu and the nu.
Well, that's another question. This has 16 terms, right? We just concluded that.
See?
But how many equations have I written down now? That's a different question. It says there are 16 terms if you would write it out, but there's a separate question, but how many equations are there? How many combinations mu and nu do you have?
4 if you eliminate zeros.
Yeah, but let's suppose that we have no idea what to do. 16?
Would it be 16 times 16?
Well, these are 16 numbers, right? This was shorthand for 16 numbers.
Yeah, but you already have 16 terms on the inside.
Yes. So what you have now is that for each mu and nu value,
You have
there's
16.
you have 16 terms.
So then it's
16 times 16 in
16
total.
to the 3?
And 16 to the 2.
To the 2.
Now,
Yeah,
for
yeah,
each
yeah.
mu and nu version that you have here, you have 1 equality sign. And at the other side of the equality sign, for each mu and nu version, you have 16 terms. So you have 16 equations.
We got it figured out, so you don't have to worry.
Oh, well, what
You can stay here. We booked a lecture hall.
Oh, okay, but
Osa must have missed the booking or something.
oh, I'm sorry, but is that okay for you?
Yeah, that's fine.
Okay, good.
Thank you, Simon.
Thank you.
Good. Thank you, Simon. Okay,
Bye.
good. So this is 16 equations, each consisting of 16 terms on the right-hand side. Now, obviously, nobody wants to write down 16 terms, 16 equations, each consisting of 16 terms, yes? But this is 1 line. Again, Einstein said this is the biggest thing I've ever done to science. Again, no physics here, it's just notation, but extremely convenient notation. Now, let's have a break and continue the discussion in the tutorial. But I propose that after the break, what we will do is first of all let's find what the Lorentz tensor is. So the actual expression. Then prove this rule, and once we have this rule down, then I can prove that this is a 4 vector. Yes. So let's do it in a exercise explanation session. But first, a break. That's how they say it in Belgium, I understand.
So you have like one. Okay, so you end up with like Lorentz.
I missed the tensors.
I am from the 100 grams of sugar.
That makes sense. I was like, what the fuck?
No,
Okay,
it's not
okay,
100.
okay.
It's like
This makes
22
sense.
grams of sugar,
Okay.
but since it's your third one,
Okay,
you
so
know,
yeah,
and you did you have a cookie at the thing?
I did.
Yeah. But it doesn't matter. Like you're using your brain all the time. So.
Yeah, but I don't know if it actually
Okay.
burns all these calories. 80 calories a piece, so this is my third. So there's
Yeah,
that's
but
not 40.
calories don't really like where the calories come from is more important.
Yeah.
No, I agree with that, but okay, but calories do not come from proteins in this one, right?
No,
it's all
from
carbohydrates.
sugar,
Yes,
yeah.
so it's actually
You get it.
Yes. Okay, I'm going to do push-ups.
Oh, but it's not 80. It's 80 per 100. So you have to go.
Years like
Oh my God, that's terrible.
What are you gonna
contraction.
do? I'm gonna.
This is about half my calorie intake for today by this one here. Oh no, well, the grown man needs about 2,500 calories per day or something like that, right? 2,500, yes. Grown woman about 2,000. So this means my third. This is 250 milliliters, 80 calories a piece.
just feel yourself
You're
alive.
prepped for the whole day now.
Well, almost. I mean, that means that this is about 200 calories.
Have supper.
I've had 3. This is my third, so that's 600 calories from the 3.
Paying here.
Oh my God. I'll get fat.
Get used to it. I'm more.
You're not fat, yours.
I'm so scared, you know. I'm so scared.
You just did one.
Hmm?
You know, again, take it.
Nope.
So
No, I'm reading.
Maybe
For the tensor, should we take the C's and B's into account?
Yes.
Because I remember that we took ones
Well,
in general.
oh yeah. We
And
took
I
the
missed
C's
the
to be
ones.
1, yes, but you can, I mean, no, whatever you do, you cannot get rid of the V's, right? The V's have something to do with your choice
Yeah,
of voices.
yeah,
okay,
sure.
but
I vaguely remember what the Lorentz tensor is, but I'm not quite sure.
It's gamma minus V over C, gamma 0, 0, and then continue from there.
very annoying.
But yes, what we did, we put the C's to 1 there. I'm going to leave them in now this time. Yeah, I know, I hate C's. They should not be there, okay? They should be 1.
Just make our lives easy.
No, people have. This is the C's. And this makes life easy, but
Mhm.
It would be more easy
I agree.
to make
crazy.
C's. Oh yeah, Gideon, and also needed to tell you from a student that you did a really good job at the presentation. And
oh, the Bonafante.
because one of the students was from Porto Mozano and she is also in my music classes.
Oh.
And I had a concert there and she was like, yeah, oh, the presentation was really fun. And I was like, oh, you met my professor, Gideon Kuku. And she was like, yeah, but he was the most fun. He walked around, he was talking like casual, you know. All the other ones were like stiff and stuff like that.
Well, here's happy to hear that compliment, but here is where
You were 20 minutes late though.
No, I was actually on time.
You were on time?
Oh, yeah.
Oh, because she told me like, yeah, he was late.
No.
You know there's a
My,
filmmaker
my
coming as well.
I had to start at a
This
quarter
says
to
even
3
more
if I'm
than
not
this.
mistaken, but a quarter to the full hour. I forget what the full hour was, but a quarter to 3. And I was there at a quarter to 3, but on my way I got a call from not the school, but from the other organization saying, well, we finish a little bit early with our presentation, so could you come 20 minutes early? I said, well, I'm now on my way. So the students have waited for 20 minutes
I don't care that
because
you're
the
Oh, okay.
other
The
presentation
other ones, okay, okay.
yeah, so
I just basically thought like, yeah, he was teaching us.
Yeah,
yeah, that is true. That is what
He
I
was
was
teaching
teaching.
us.
Oh, I also talked to Ronald yesterday in Zurich. He said, "What are you supposed to do electrodynamics with these people?" And he said, "Oh, yeah, I forgot."
It's okay.
No kidding.
And he felt really sorry too. He said, "Oh, I feel so bad now."
We have two
Yeah.
students who
Yeah.
are buying our pizzas now.
Yeah.
What if
I think I
he-
missed something. What?
Yeah, yeah.
I found my song.
They're pretty romantic.
Oh, yeah?
Shut
They're
up.
pretty romantic already?
Yes.
Yeah.
Oh, Giovanni, what are you
I found
talking
my
about?
No, they, and not me.
They, me,
You just comment.
they.
But romantic is a compliment. You shouldn't shove it up to
No,
somebody
no,
else. You
yeah,
should
yeah.
take it. You say
Oh.
yes. Okay. Well, but okay. Listen, romance is more. It is not the idea of candlelight and rosebuds everywhere. I mean, the rose petals. Don't ask me what it is. I have no idea.
I never knew love in my life. I never knew it.
You're just jealous of money. You want to be a romantic
No souls. People with no souls don't fall in love.
You can be. Hey,
I know.
it's fine. It's okay.
I have my
I
own
think
true
you will
love.
like him as well.
Unless you go and study
Married
physics in
three of
India
us,
and
you
you
know?
meet your
Yeah.
physics
think it's
teacher
gonna be great fun.
soulmate that is vegan and vegan and what?
I
What
found
else
my,
was amazing about him?
This is about my life.
He's 60
I'm
years
sorry.
Yeah,
I should have.
yeah.
He's 60, but I don't care. You know, it's
60
knowledge
plus,
is
it's okay.
beyond.
Mature, but fine.
I'm going to stay out of this one.
That's maybe the smartest.
Yeah,
choice.
No, I emailed some guy for my thesis.
I don't care.
He doesn't want to know.
Fine, I'm going to shut up now.
Okay.
But he's vegan, so.
Important.
That's the best part.
Oh, sorry. This is for thesis purposes.
Yes.
Okay, then I'm interested.
Yeah,
Okay, yes.
exactly.
Okay,
it's
good.
not,
Okay.
It's not actually.
No, it's
but
just the
then,
word romance got me on the wrong track. Okay. Good. Okay, what is
Because
it? Seriously, what, thesis?
Mhm.
What
Yeah,
about?
but he is no longer at the university. So I want to go to New Zealand or Australia, but he's no longer working there. However, I'm going to a physics camp in the Himalaya that he's organizing. So it's
Really?
super cool, yeah. So that's why I am very enthusiastic about this. And Sky.
I'm interested. A physics camp in Himalaya, of all places.
I know, yeah.
No, it's
yeah,
cool. I would
really
love to go there. It's just that I wonder. Usually, you have these things at universities,
Yeah,
ground level.
Yeah.
Cosmic, cosmic
That's what I like about
Some
it.
rituals.
chakras, whatever.
No, is that the case? Is it some
chakra.
Nepal monks thingy that's going on there?
To
It's,
find the
it's
answer to
just,
the
in nature. In nature setting
And then
with
you
a
have a
chalkboard.
voice in your head.
But it is a
It's,
good
uh,
physics.
Just out the
Just get your voice.
Physics.
Yeah, this guy is
Give up physics.
so he's
only
done
one
a lot of
today.
research
That'd be
on
good.
That would be me.
and on
Yeah, that's really
Australia.
offensive.
Yes.
And you
And
don't usually
on-
touch
yeah, he's still doing research on that because he thinks it's probably gonna be for
Yeah, but I said like
a
one
young
woman,
class that
you
doesn't
know.
Cross the leg,
And my boss
And so he's written like a book about it.
Why was this so fine and nonsense?
Trying to.
Can I drop the word? Is it Majorana particles or something like that? Does it something?
Yeah, I think so. It's I don't think it's much. I think it is actually Majorana particles.
Yeah.
Okay.
Yeah.
So neutrinos do not satisfy the Dirac equation.
No. It's so he separately neutrinos, but fermions. So a type of fermions. But I haven't
taking
really read
X
into
right
everything.
But
because
I'm already
I'm
discussed with him that I want to
first
go to Nepal for
updating my
theoretical
particle
physicists
physics
and
knowledge
also probably some
within
gravitational
2
waves
months. I have 2 months.
calculations
It's
on
fine. 2
the
months fine. I can do 2
Einstein
months.
element.
Oh, yeah.
So it's a physics camp, it's 2 months, or is it
Yeah.
physics camp?
No, the physics camp.
You can just
Wait a minute, you're in your third year. I mean,
Yeah, I'm going to
I
you
should,
like at the
I
end of
should
the
be
year.
doing
I
my
only have
thesis right
2
now,
days
correct?
that I
But
have
I'm
to
not because
teach
I want to more
teach
time.
the children in high school, and then for the rest
Do
of
the
the week I'm
practical
off. So I'm
and
going
do
to ask
other
him
courses, but I'm
if I
not
can
doing
have
other
some extra
courses.
practice, extra material to be
Online
ready
courses
for
and
next
stuff.
year. Then I can like prepare
But now it's
myself
actually
maybe
good
like
because then
create a
in
little
May I
project
can
for
go, and otherwise I
maybe,
wouldn't
but I'm
have my
not sure. I
thesis.
don't take that much
So now I have my
responsibility
thesis
on
in
myself.
September.
But maybe do that.
Yeah,
and
do
do
it.
that.
Because like it's also easier if you do
No,
like
no,
this
I'm
is
gonna
an
have
ideal
that Skype
project
call
that's
with
really
Yeah,
you.
then you
Well,
can
actually,
show
I
like
found
I did
because
shit.
I
Yeah,
know
yeah,
from
exactly.
friends from
But I need to
I
ask
met
them,
my Ali at CERN because she went there.
because when
Yes.
students at Cambridge, we have to hand
And
in
this
a
guy's from
proposal
Australia and
before
he masters there and he has some contacts
yeah,
from
senior.
Oh, good.
Yeah,
Yeah,
so I'm
so
gonna maybe next year I can do. I have some time.
So you,
At the project
that means
and
you would
like
like
that.
physics
Because
go
then
to
it would
Australia and
be
New
this
Zealand.
would stay
physically
not
be
this
very
semester
Yeah,
last
yeah.
year, but the semester after,
I think it's
in
nice.
September next year.
No, in
Is it still on
February.
fire?
So I can maybe do that
Hmm?
project like
Is
in
Australia still on
February
fire?
or January and then
Yeah.
start
Yeah.
it in
Yeah.
February.
Yeah, that's fine.
Okay,
Still.
yeah, that's
Fuck.
She's like,
you're
but
able to
Jesus.
Yeah.
I guess if you do some programming, you'll be
Yeah,
able
that's
to
program.
Yeah, but I also have family.
I'm doing the big
Yeah.
data analysis.
Yeah.
I'm like,
What
am I doing?
It's gonna be like
Oh yeah. When is the deadline for the
Yeah, I
big data?
I discussed with Jacob. What is 1 week?
No? No, continue.
the
continue.
motivation.
Officially, Monday and Tuesday are carnival. Yes, so those are official holidays. Now, the other days might be lecture-free days, but they're not official free days. So, which is another way of saying, yes, you might not be physically required to be anywhere. You are still physically required. Well, you're not required to do anything, but we have the right to give you work to do on that day, whether you do it or not. So it's not like a Christmas vacation for a week or something like that. So I think a reasonable choice would be Friday, because that means you get it. So the deadline to be that Friday of that week, because then you get your 2 days back plus 1 extra.
Okay.
So you have 2 official holidays. So those you certainly should have, and because all of us are nice guys, we can add an extra day to it. I think that's reasonable.
It's like everyone, he's gonna give 20.
But I have to send it out first. But I did yesterday in Switzerland discuss this with Jacob, what we should do about it. And he also said, oh yeah, of course, yeah, the carnival thing. That's the thing.
And so
Gideon, I sent you an email about the power spectral density files.
Oh, I didn't see it. Okay.
I just wanted to know what the columns meant, because each file has a different column.
Yes, all of them. Well, the first one is the frequencies.
Okay.
So the X values, if you will, and all the other columns are the Y values, but depending on exactly. So all of them are sensitivities, but sensitivities due to other physical effects. The last column is the total sensitivity, so that is the one you should.
So we should always take the last column and the first column for the frequency, and the last column for the total spectral.
Exactly.
So always
the first and the last.
First is the X and
Yes.
the other one is the Y.
Correct, yes. So one of the columns is due to seismic noise, one of them is due to quantum noise, blah blah blah, and the last one is the total one.
But yeah, I think
Is
he's
the
amazing, and I
Rossby
didn't
also
even tell
taken
him
in
I'm
account,
vegan,
or
and then he told me
no,
he's
No, that has nothing to do with the
that,
spectral density.
Okay,
can't
that's
The
true.
Rossby modes has to do. The spectral density is a feature of the machine, and the Rossby
That's
modes is
like-
a feature of the source.
Yeah.
They do not appear in the
nature.
spectral densities.
Is this the correct answer?
Yeah.
Yes.
But he
So I
he's
agree
from
with
the
that.
University of Cambridge.
You already have it?
Yeah, I hope,
And,
yeah.
so he still does research there.
So if you will, this is an exercise in reverse.
But he also has
In
an
reverse applying the contraction rule, right? Because usually what you do with a contraction is that you know what the tensor is and you then write it out. This is the other one. You know what the contraction is, what should the tensor have been?
Vegetarian implies the idea
I
that
think
they don't eat egg,
I think I
and they still
could
eat
have.
milk.
Well, let's do it here.
Yeah.
Let's wait until Raquel is back.
Yeah.
And do that.
Because the idea is to not hurt.
You lived in Amsterdam, right?
Yeah, I was born and raised here. Now, not just at one point, I lived there for 35 years.
Yeah,
Where-
but I
where
think
did
he
you
has
study,
good ethics
like, for your
and
bachelor's?
morals, as far as I can tell, which I find very important.
What age,
Like
what year?
physics, okay,
Ah, very
that's super
I know, I
interesting
said
and I love
where,
it, but I like
but,
the fact that it's
all of
not
it
only that.
Okay, is it
And all the participants have to read like this
Food
literature.
Right now, the bachelor's
Of,
of
Herman
physics of the 2 universities now is
Ah,
a
really?
combined
Last
bachelor
game?
masters in physics.
Yeah.
But back in my day, there were still separate ones. I studied
Never?
it.
Yeah.
In fact, I started at
Yeah.
UFA,
I like
but then I switched to free
the
my
Glass
second
Peak
year,
game.
did my bachelor's and masters there.
I think it's good. As far as what I've
for a
seen on the
PhD, I
internet,
also
it's good, but I'm gonna read it.
at NICAF.
right? Okay.
I was completely
Yeah.
Is it like nice?
Nice.
Like,
Yeah,
I don't
Janus
know,
for some reason,
I'm
that
looking
is
at
interesting.
but,
Yeah, but this is just May and it's summer.
yeah, I'm not wondering about
it's
housing
amazing.
rate because
Yeah.
Amsterdam is more expensive.
Yeah, I know, that's true, it's expensive.
Summer I'm
Yeah.
gonna, yeah,
It's difficult for
what am
people
I
usually
gonna
to
do?
find housing.
So you actually don't have
Usually
any
people
courses
find
in,
housing, but it takes a while.
Yeah.
No,
okay.
I'm gonna drop off.
Yeah, but yeah,
I
it's
used to,
not really
I plan
expensive.
on doing
Right.
statistics, but you know.
Now, in my particular case, I was born and
What-
raised
what
there,
are the-
so when I turned
a
18,
semester of
I
almost no
had a-
courses. If you have all
one of my very few flashes
Yeah, I
of
have
instruction
enough
that I thought, let's
credits,
go
yeah.
to
Then you can just
the
do
municipality and already
Yeah, because I didn't
uh,
need this semester in the first
uh,
place.
put in a search for a house because I knew that would typically
I'm
take
done.
about 5 or 10 years, and I
Yeah.
thought
My
you're only eligible when you
Yeah.
turn 18.
Yeah,
So literally
exactly.
the week after I
How
turned
it
18, I went there and said, I'm looking for a house. And then
It is.
5 years later,
It is.
I sort of
but
finally
then
became
again,
eligible that I actually got a
I was
place.
planning on doing courses.
But once you're in the system, the
But then
social
next
housing
time.
system, then in principle you're set for life. As long as you don't leave the system, they cannot kick you out of your house unless you do something really bad.
Break the
So-
system, huh? Yeah.
What did you do
I'm
for
glad that you're in
masters
love
in?
with your
You did it at UVA, right?
Yeah.
Are you coming back after May?
Because I'm looking at masters
Well,
and I'm
officially no.
Yeah.
freaking
Yeah,
out.
I
I'm
wanna
stressed
stay
about
with-
everything.
Depending on-
I don't know what to do.
So it's okay. It's an issue of choice. It's not an issue of difficulty.
Yeah, I'm pretty sure that I want to go to UVA because they have the astrophysics and
That would be your.
yeah,
Yeah.
and then they also have just theoretical physics. But I don't know.
Yeah? Oh, in May.
Well, it's
From the
different.
other
I mean, there's overlap, but it's different.
But
I did
I make
theoretical
money
physics.
now, so that's
was
why.
my
That makes sense.
But I did it
Probably
in
flying together in
theoretical
Himalaya is
cosmology,
not
so that was
cheap.
very close related to both. By the way, that distinction between Grappa and theoretical physics back then didn't
I
exist.
promised
There was
myself
just
never
one
fly
master of
again,
theoretical
and
physics,
then
and you chose a topic within it. Right now they're separate
Yeah.
masters.
That's just.
Are you also flying
Yeah, well,
inside
it depends.
India?
Depends on whether you want to apply
Yeah,
your
I have
theoretical
to fly
physics
like
or do you want
17
to
hours.
alter the theoretical physics.
Well,
If
you
you-
compensate with
If you want to become a
Yeah, that's what
researcher,
I
become
said.
knowledgeable
Well,
about
that's what I say also
why
with my vegetarianism.
theoretical physics is the way it is, so that later on maybe you can think about making corrections or
Yeah, I
For
know.
you
combining
more than
gravity and
all of
quantum mechanics or something like that.
transportation and
Then
all the
I
things
know,
combined.
theoretical
I
physics
already
will be
know.
a
That's
master.
why I
Because that is really
So
about
it's okay,
the
yeah.
fundamentals of
But
theoretical
then still you
physics.
can't just say
Whereas
because
the
I'm thinking
Grappa
I can now scroll
uses the
rest of my
fundamentals
life.
and calculates stuff, which is
I
still
mean,
theoretical
flying
work, but
sometimes
it's,
is just like
the goal is
The
different.
goal is different, yes.
Yes.
Unless you want to take the class to go
Or
to
you just do,
Himalaya.
you have a number of
And
electives in
then
both.
Himalaya.
You have a number of electives in both, and you just choose
Yeah,
one of them
I'm
and
gonna-
use the course of the other one
And that's
as
I'm
the
gonna swim
electives.
there.
Row.
So you can
That's
sort
a
of make a
bit-
linear combination.
Oh yeah.
Okay.
Oh yeah, it's so expensive.
Possibilities.
I'll see you later.
Yes, bye bye. See you at dinner.
Bye, Merlijn.
Bye.
Bye. Thank you.
So, I'm sure Raquel is on her way. We're almost done with the full argument, but I propose that we use part of the tutorial just to couple of these and then build our way towards it. I think this one we can easily do right here, right now, in the group setting. Yes. So, the question is, this guy is a block, if you will, of 16 numbers. Now you might notice that I'm not using the word matrix or try to avoid it, because you might be tempted to think that any block of numbers is a matrix, but just like any column of numbers is not a vector, in the theoretical definition of the word, not any block of numbers is a matrix. It's a tensor. If you want to know what the tensor is, feel free to ask, but it's not for now. Just saying it's not a matrix. Anyway, you have 16 numbers here. The question is, what should these 16 numbers be such that if you write out this contraction, you get back to Lorentz transforms? So maybe it's good to first remind ourselves what the Lorentz transforms are. Now Lorentz transforms are 4 of them, right? Because time changes and the 3 spatial directions change. So let's first write down what the Lorentz transforms are, so it's something to compare to. So if you would not use the contraction notation, but write everything in terms of just 4 separate equations, one of them being dt squared, yes, with a c. Do you remember what the corresponding Lorentz transform was?
Just for dt or dt squared?
I should have written this, or just for t dt.
It's gamma brackets dt plus minus v over c squared plus dx.
We derived this in special relativity. This guy. Note that we are now already assuming that the 2 coordinate systems, inertial systems, are moving in one particular direction with respect to each other, right? The v goes in one particular. Which direction is that? It's the x direction, yes. If it had been the y direction, fine, then this had been a dy. Now let's write the Lorentz transform for x. Again, just
dx plus minus v times dt.
correct. And we never, or we usually don't write these out, but let's also write out the
dy and dz.
yes, because Lorentz transforms only work in the direction of relative motion between the 2 coordinate systems. And we already saw it's in x direction, so that means that the y and the z are in the same direction, or stay the same, right? The y's and the z's are not affected. So, there we go. Okay. Okay, so we have our four Lorentz transforms written out, but the question is, I want this information squeezed into this one line. Let's make life simple. If y and z are not going to change, they should just be 1, right? I mean, how do you get y primed or dy primed? Well, you just take dy and multiply it with 1. Okay, so that means the part where the y and the z is multiplied should be this block. Okay. This part, right, it's 16 numbers, but the 4 numbers here in the corner will make sure that these do not change.
Also, you can fill the rest of the
Yes, you can also fill out these. All of this, what I've now put in, all of that makes sure that these two are the way that they are. The zeros simply mean, if you think about it, a zero here means that this is t, x, y, and z. T, x, y, and this is and this is t. This means that the t and the y do not mix. They don't feel each other when you do a Lorentz transform, which is true because they don't. There's no t and y combination anywhere. And this one means that the, let's see, txy, that the y does feel the y. How much does it feel it? Well, with the same, with 1. Okay, so the numbers have a meaning. It tells you in the Lorentz tensor how, when you go to a non-inertial system, the numbers start feeling each other. Sorry. It's a hand-waving way of putting it, yes. Well, how's this? How much they mix, right? Here, t and x mix with each other, x and t mix with each other, y and z do not mix with anything else. Okay, but then we have only 4 numbers to fill. What are those numbers?
Gamma plus minus gamma v over c,
Okay.
plus minus gamma v over c gamma.
Let's put it in terms of mixing. This number should tell you how much the dt feels dt. Now let's look at the equation. How much this dt feels that dt, but how much does it feel it?
Gamma.
Gamma, okay, very good. This number, it tells you how much dx and dx feel each other. In other words, how much this dx feels that dx is by gamma. Okay, 2 numbers to go. This number tells you this is dt dx. This is dt dx dt. This is how much dx and dt feel each other. So how much this dx feels this dt. How much is that? That will be plus minus. So this number is plus minus gamma v
over c.
Why is there an over c?
Because you have also there c.
It's this c is what you mean, right?
Oh yeah.
Okay, well.
That's only for the other one.
Yeah, but we're going to make a point of this in a moment.
But
So
because the 4 vectors come with c.
Exactly, I haven't taken that into account, but I will do so in a moment. So this will be it. Yes. So this is your Lorentz tensor. And I hope it gives you a feel for what the numbers apiece mean. It means how much mixing goes on if you go to a non-inertial system. That's really what they mean. Now, those pesky C's, I hope you mean, I always make a joke out of this, but I hope you see that at some point they really become a nuisance. Definition-wise. Now, the dx's here that we have to contract, I'm using the words now, I'm going to contract this tensor in a moment with this dx. And dx mu is c dt, the c is defined to be at that place, dx dy dz. Yes, that's the definition, that the c actually is part of that 4 vector. But that means this should not have been dt. If you want this to be part of that 4 vector, this one, you're missing a c there. So it would have been better if we had put the c there and had put the c there. And the same thing here. So
and then 1 c drops out in the first line.
Yes, it does.
Plus minus v over c.
Yes, exactly. then here we're going to this dt gets replaced by a c. This c drops out, and then you see that both have a vc, and then it becomes beautifully symmetric. Then both of them come with a v over c. I haven't done anything. I'm not smuggling my way towards an answer. The only thing that I did from the one that we wrote down before to the one where some c's are replaced is taking one of the c's and putting it in the definition of the 4 vector. That's the only thing that I did. Now, again, this is why we just drop the c's altogether. Just to so we don't have to constantly ask each other, are we defining the c as part of the tensor, or are we defining it as part of the 4 vector? At some point you don't care. If there's a c somewhere, fine, let's put it here. Okay, now I'm going to leave the c's in, despite me not liking them, just for completeness sake. We're going to define, it's a choice that we make, the c as part of the 4 vector. You don't have to. If you leave it out here, that's fine, then you have to compensate with these c's here. Yes? And then you get the original version where you have c squared here and no c at all here. We are going to define this, a choice that we make, c as part of the 4 vector. 2 benefits. One of them, the units are the same in the 4 vector for all components. Right? It's all meters now. And secondly, the Lorentz tensor becomes nice and symmetric. Again, it's a choice. Other choice works just as well, but this is the choice that we make. Good. Now, if yes.
I'm sorry. So then, wouldn't one of the c's underneath go to square?
No, it drops out.
So then, wouldn't one drop out completely?
Should we just try a couple of these numbers in the contraction, so we also practice with the contraction a little bit again? Okay. And then you will see that the c's as they are right now are actually correct. So let's just do an example of this, yes? So by looking at our mixing argument, how much do the numbers mix, we could find the Lorentz tensor. Let's do a check. Let's not check all 16 numbers, right? 16 combinations. Let's try one of them or so. Shall we see if we can get this equation out, or which one do you feel like doing?
Yeah, the first one.
The first one? Okay, so what we're going to do, our strong guess is that the Lorentz tensor will look like this. Let's see if indeed our guess, when put in our definition, our new rewriting, if that indeed gives us our Lorentz transform from period 2 special relativity. Alright, so let's see if this one works. Okay, thank you. Let's do it right here. Oh yes, and it works like a charm. Good. So if I'm going to want to check this Lorentz transform, right? The first one. Which mu am I taking out then?
0.
That's a 0. Okay. So I'm looking for dx0 in the prime coordinate system. Now I'm just blindly going to copy this guy here. I put mu to 0, then this mu is also 0. 0. This nu is a contraction. So for the nu's, I have to apply this rule now. How many terms would I get if I would blindly write out all the new possibilities? 4, right? You get 4 numbers plus plus plus. Now you can write out the 4 numbers. Let's be clever about it. We have mu is 0, that means we are in this row now. And of the 4 numbers, 2 of them add nothing, right? This one will add nothing, that one add nothing. So in this particular contraction, these numbers will not add anything. So we really don't have to write out the full contraction. You just have to write out the first 2 ones. Now, you tell me, what are they then? This is 0, 0, dx0, right? And then there's 0, 1, dx1. And yes, there's also a 0, 2, dx2. But then you get the 0, 2, and the 0, 2 is 0, so it doesn't add anything. So that's it. Now let's put in our Lorentz tensor. What is gamma 0, 0? Sorry, not gamma, lambda 0, 0?
Gamma.
That is gamma, yes, that's probably where I got it from. And dx0, what is that?
CDT.
That's CDT. Plus, what is lambda 0, 1?
Plus minus gamma V over C.
V over C, correct. And what is dx1?
Yeah.
That's dx. So if and dx prime 0, what was that?
CDT dash.
CDT prime.
CDT prime. Now question, if we take our guess for our Lorentz tensor, we put it into our contraction, does it give us this? Is the answer yes or no? This is what we found. Is that this guy?
Yes.
Yes.
It completely is, isn't it? So your question was, are the C's correct? Well, apparently they are.
Yeah, something.
Well, it's an example.
As an example, because you have 15 more numbers to go if you want to do the full check. But yes. Now, I got the answer. This is the right Lorentz tensor. Good. So we have combined the 4 Lorentz transforms all into one very economic equation.
Beautiful.
This is also the tipping point where you're
Sorry. I think we got it at the same time. Okay, nice.
this is the tipping point where your notebooks start to look very smart, right? With all these equations that don't have any numbers anymore, not even plus minuses. It's just random symbols in Greek letters.
I've been texting my biology friends, like freaking out.
Good, we
Oh.
have
Okay, no, it's good.
good.
Thank you.
Okay.
You're welcome.
Wow.
So we have now taken 2 results from special relativity period 2 and written it into a new notation. First of all, Minkowski line element itself. Secondly, our Lorentz transforms. How about this one, just for funsies exercise? E squared plus p squared, e squared is p squared c squared plus m squared c to the 4. One other equation that we derived. Shall we write it as a contraction? You guys do it. Let's see what we get in a couple of minutes. We derived this in special relativity. Claim you can also write it as a contraction. I just wonder what contraction is.
Does that have a 4 vector?
Yeah.
Here's our 4 vector, so you have to define the 4 vector.
So P can be in X, Y, and Z. Momentum can be in different directions.
Yeah, but this is the square of the length of the 4 vector. So it's yes. So see if you can write this guy now as a. Can you write this as a contraction? So what I'm looking for is some 4 vector, some matrix, quote unquote, tensor, times another 4 vector. I want to have it in this shape. Something contract with something else. Can you make this in that shape, that form? Just a hint. First try to think which 4 vector you need to use. How does the 4 vector look? It's not CDT, DX, CYDZ. which four vector to use to begin with?
Momentum.
How would you write it?
E divided by C. Px. Py dz.
Giovanni's suggestion is use this guy as your four vector. The notation wise, you put a mu there. Is that a four vector actually? It's four numbers in a column, but is it a four vector? We made a point before that not any four numbers in a column make a four vector.
They have the same units?
They certainly have the same units, so it's necessary, but it's not sufficient to prove that's it. But that's correct. They have the same units. That's what the C takes care of. But is it a four vector?
Mass is invariant.
Mass is super invariant.
C
Yes.
is invariant as well.
Yes.
So if we move P on the other side of the equation, we are left with the magnitude of the four vector is equal to m squared C to the power of 4, which is invariant. So also the magnitude of the four vector is invariant.
I'm missing half of the argument, I feel.
So if we move the P on the equation, if we move that on the left hand side, we know that the term on the right hand side is invariant. Therefore, also E squared.
Good. Good. So for everybody, if this is a four vector, it must obey the Lorentz transforms. The Lorentz transforms for this guy would be that E squared minus P squared is invariant. And it is, because we proved it in special relativity. In fact, we proved that this is mass squared. And mass itself is invariant. Okay, so we know that this guy is a four vector. Good. So it's not just four numbers in a column, it's really a four vector. It obeys this rule on the left hand side board. Okay, good, then we're almost there. Then the question is, can we write this equation in some contraction form?
Is it possible to just change the variables from the old four vector to the variables of the new four vector?
Yes.
So would it be p to the x mu new mu equals
so p to the x?
Sorry, to the subscript x, not p.
Yes.
Yeah. To mu prime.
Maybe you can write it down. You're probably saying it right, it's just
Yeah.
it's much easier to just write it down.
I'm not sure if this is right, but and here's a contraction.
Let's see what we have here. Comments from people. So if I understand your reasoning, does this P mu follow the same Lorentz transforms?
Yeah, are they interchangeable?
They are, yes.
So the same Lorentz tensor works with these?
Yes. So, but then he wrote down this.
That doesn't really write the formula from a book, no?
No, that's one thing. I mean, it's towards that formula. It's not the formula itself yet.
Because that's how you transform the
Yes.
the
Exactly.
momentum.
Exactly.
So that's a momentum.
What you've written down now is how somebody's four vector for P transforms into somebody else's four vector. So to make things visual, I mean, there's something moving about here, and I measure its energy, and it's four three momentum numbers. I get four numbers. Now I go to another coordinate system. I now measure those four numbers again. I get the same four numbers but with a prime, and then the old numbers and the new numbers are related by this relationship. That is correct. So you have to write transformation properties. Small comment, when you write px, px is this one, right? But
shouldn't this be d?
This px would be when mu is 1. Your notation is slightly ambiguous because the mu should pick one of these four numbers, and you do it by both saying x and mu. So this is redundant. You don't need the x's there. Okay, but this is a transformation for momentum. By the way, that 4 vector is called 4 momentum. You really like a 4 dash momentum. Yes.
We have to create a new tensor then, don't we? Like if we, so this is a bit like the same formula as the Minkowski line element.
Yes.
So there you have the other matrix with -1, 1, 1, 1, 1. So the thing is, like, it doesn't really, you don't get this equation really.
No, that is indeed a point. From this, you don't immediately get this.
Yeah, but even so, I tried to have like this new matrix with c squares, and then multiply. So say that this, so it would be like p mu and p nu. So you have like this new matrix that contracts p nu and p mu.
Okay. Yeah,
and then, but the thing that you don't get like this sort of equation form, you get like this.
This is certainly one way to go, but to point out what you wrote down is a correct formula. What you wrote down is that if somebody measures these four numbers about some physical system, and some other guy who sees the same physical system from a different inertial system, this is why moving with constant velocity, then my four numbers and the original guy's four numbers are related in this way. So it's an answer to a question, namely if the question was how do my four numbers translate to somebody else's four numbers, this would be the answer. It's correct. But the question that we try to solve with this equation is not how do these four numbers relate to some other guy's four numbers. This equation tells me how my first number relates to my other three numbers. Right? This equation tells you how this E is related to these P's. So the whole question about, but how does some other guy see it, does not come into play. This is all about me and my own system. So it's the correct answer to a question, it's not this question. And then, so I'm going to go with Jonas's. Can you say one more time what you want?
Actually, actually it does work a bit.
Okay, no, but actually then maybe...
No, but it doesn't really work.
Okay.
Almost works.
Okay.
Should I try?
Do you have to rewrite it in this way? With these two tensors and the two etters?
Yeah, I didn't see it either.
Yeah, it makes so much sense.
Can I try?
You're probably saying a good point and just not seeing it. It's a statement about me.
Do you have to rewrite it in this line to get like
rewrite it in any way that you want as long as this comes out. Okay?
I can try, but then you might need to help me for the first one.
Well, we are a group of smart people, and there's also me, so I'm sure we can figure this out.
So humble.
It was sincere humility, yes? Humbleness.
Sure.
Okay, yeah.
Plus m squared c4. And the thing is that if we use this, so p mu being equal to e over c with px, py, and pz, then we could write something as being a sort of other matrix, so I don't know how to, well, let's call it a pi matrix, with mu and mu times p mu and p mu. But the problem is that and the pi matrix could be something with like a lot of c squares and zeros everywhere. But the problem is that here we don't have the energy. This part is not solved, so we just have to find out how to do this.
Okay.
And I don't know if that's correct way to do it.
Okay, let's Let's see if we can figure this out. So I will narrate because I think your argument is, well, this equation that we have to write as some contraction. If you write this itself out, knowing that p itself is px squared, py squared, pz squared, this is just that, yes? No contractions yet, it's just writing out p squared. And then your point is, well, maybe you can write this as itself a contraction. In fact, it's a double contraction.
Yes.
And why? I guess your argument is, well, because you need p squares, so you need at least two p's.
Yes, exactly.
So that means
I didn't go
this
all the way down.
Okay, no, you were doing fine. So this will not work, right? This contraction is one contraction will not work because the best it will give you is single p's and not p squared. So you have no choice but to guess that it must be something like this. And this is what you wrote down.
My problem was to convert this into something that would give. So E could be mc squared, but that's just the formula. Yeah, exactly. That doesn't work. So I don't exactly know. So I think that would be a correct way to go, but I didn't bring my thought until the end to manage to actually make this work out with the matrix in this.
No, but I do see the point. What you say here is I need at least some p squares and an e squared, so I need at least two p's. And there's to be a matrix. It's a tensor, it's not a matrix.
Sorry.
Yeah, they look the same notation-wise, but they're different things. Anyway, it doesn't matter. Something needs to be put here. You called it the unknown pi matrix at this point. And the question is, what should this pi matrix be? Yes. Correct, yes. Alright, yes, a tensor. yes. Okay, but I'm going to give you one back because you said I have to multiply this with that.
Contract.
Yes.
Sorry, contract.
And that really isn't just semantics. A multiplication is two numbers literally multiplied. A contraction is multiplying and then summing. It really is a different thing. Anyway, but yes, your guess is if I want to write it as something, it has to be at least two p's. And you have to contract it with something, and then you have no choice because you have two p's have a double contraction. So it should be something like this-ish. The question now is, what is this big pi tensor?
Yeah.
Okay.
So it could be like the momentum tensor or called something like that. But I don't. This is very wrong, and it doesn't work.
But it's actually quite
a good
close.
starting.
Yeah, it's a very good starting point. If we can find some pi tensor that will make this contraction turn into this thing, then we have solved the exercise.
We can maybe take already the c's to the other side as well. Then we have e over c.
Yeah, but we don't know what the c is yet. This is his.
Yeah, but I mean in the beginning formula.
Here
like e.
Here.
Yeah.
Yeah, just take the c's to the other side.
Ooh, and it makes e.
And then it's already a bit easier.
Yes.
So that's the same one. Now, one thing I'm just going with you. Yes. One thing that if you write this pi tensor here, one thing I know is you never have any mixing between py and px, for instance. And there's no mixing between p and e. You don't have any combinations where you have a 1p multiplied and now really multiplied with another e or a p with a px. So it means the only p's that go together are the px's, the py's, the pz's, and the p0s.
That's why you have the diagonal.
So we already know it should be a diagonal tensor.
Yes.
Good. Okay, so that really reduces our problem because we now don't have to look for 16 numbers, we only have to look for 4. So what are those 4 numbers is now the question. Well, one easy way, of course, would be just to write this out.
Oh, it's -1. Okay. No.
Go ahead. So close.
So because on the other formula, to move it on the other side, the EC squared, you need a minus. So so if you want to have this one formula with EC squared on one side, it's E squared over C squared. On the other side, you would have a minus. Yeah, or yes.
Yes. Okay.
And so you could have 1 and -1. It doesn't read. Yes.
If I do this contraction, if I do this double contraction now, then the p0s come with the 1. Yes. And p0 is e over c. This writing this out will give me e over c squared. Minus, each of the p's. squared, px squared, min py squared minus pz squared, 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 squared. All of this together is p vector squared. So what you wrote down, this thing, is the same as EC squared minus P vector squared. Should be equal to what?
M squared.
MC, yeah, M squared C squared.
I think it should be a minus.
Oh yeah, MC squared.
Like it's minus C over C plus.
Are you not missing an M? Like M squared?
Yes, this should be an M squared C squared, yes. Okay, now, so Jonas's suggestion, this thing is the same as EC squared minus P squared, and the thing that it has to evolve into, it should be equal to M squared C squared. So, if you want to write this equation into a tensor form, contraction form, sorry, take Jonas's pi matrix, and set it equal to M squared C squared, so that's the same as this.
But you can simplify it into the normal, the other one, just by putting the minuses on the opposite
Yes, if you put the minus here, so there's another minus there, that
then
means
it becomes just
minus plus plus plus, and I think this one before we got Minkowski tensor.
the Minkowski tensor.
Nice. There you go. Beautiful. It is. So, how did we solve this exercise? Thank you, by the way, super contribution. By the way, Mick is yours as well. It's just an answer to a different question, but it was the correct answer. This equation in contraction form is the double contraction of the form momentum with the Minkowski tensor, and set it equal to minus MC squared, M squared C squared. So that's it. Yes?
You have a question.
Sure.
So you have a vector with 4 components.
Yes.
If its contraction with the Minkowski tensor gives you something invariant, then does that mean that this vector is a 4 vector?
Yes. In fact, that's another exercise I wanted to do with you, but we're almost there now.
What did you say?
Yes.
So if you have a random vector with 4 components, and you do the contraction with the Minkowski tensor, and you get something that is invariant, like here we get the mass and the speed of light, which is invariant.
He says this is invariant. He's correct. Yes.
And if that happens, then that vector is a 4 vector.
So his statement is now this. What we now did was we knew that the form momentum is a 4 vector. And what we find is if you take the 4 momentum contracted, double contracted with Minkowski tensor, in this example you get something that is invariant. Yes? But his question, does the reverse also hold? If I give you 4 numbers and I do a contraction and it gives me something invariant, is that enough to conclude that 4 numbers is a 4 vector? What we now have is the opposite. We have a 4 vector and we find that the outcome contracted is a invariant. Doesn't work the other way. If you have an invariant, you go back. Doesn't mean that the thing that you started with was a 4 vector. What does your feeling tell you? Feelings do not matter much in physics. Waiting for a response here, but okay. What does your intuition? How's that? What does your intuition tell you?
Yes.
If you have 4 numbers and you do a double contraction of those 4 numbers with the Minkowski tensor, and the outcome of the contraction of your 4 numbers with Minkowski tensor is invariant, does that mean that your 4 numbers was secretly a 4 vector to begin with? Yeah. Intuitively feels right. You have to be careful with these sorts of argumentations, yes? Something leading to another, A leading to B, does not mean that therefore B also leads to A, yes? In this case it does.
Can we prove that?
Yes, we can. Okay. I propose not to do it here. Feel free to do it on your rainy Sunday afternoon, but the statement works both ways. If something, 4 numbers, double contracted with the Minkowski tensor is invariant, then the 4 numbers were a 4 vector. Wait a minute, doesn't it bring us very close to proving that it's a 4 vector? If we can prove that this guy contracted with, if we take these 4 numbers together, and we take its contraction with the Minkowski tensor, and we find that its outcome is invariant, then that theorem will tell you that that was the 4 vector, right? Well, that was the goal for today. That is the proof. So thank you. We have now a criterion to prove it. Perfect. It's bringing me a little bit of the narrative that I had in mind, but the comment was so good that I feel that we maybe should divert this a little bit to go with that exactly. But your original plan was to prove this first. Yes. But your comment almost gets us there without proving this first. It is important that you have shown this for yourself at some point, but
we can do that as homework for tomorrow.
Yeah, maybe that's a good idea. Let's do that. So let's continue with his comment. Yes. This is just messy algebra, little physics there. Let's go with the more physical line of reasoning here. Let's assume for a moment that four numbers contracted with itself. If it is the outcome is invariant, then therefore the thing must have been a four vector. If we take that criterion, that means that this hopeful, prospective four vector, that we can prove that this guy's contraction with the Minkowski tensor, if the outcome is invariant, then your argument will tell us that this was a four vector to begin with, and we're done for today. So let's do that. Let's go and do that. So forget about this. I have to change my narrative a little bit, but that's fine. Now, while you guys think about this, I'll go to the bathroom. So maybe you can think a little bit about how to set this up. Let's see if you can take this. So take this guy, put some columns, put them in columns, and make pretend that it's a four vector. Take this guy's contraction. In fact, let's call that the A mu perspective four vector. It's actually what its name is without the perspective. It's a potential four vector. We haven't proven it yet, but we will see it. But let's already call the thing by its name. The zeroth component is the scalar potential, and the other three components are the vector potential. Used to be kind of strict, yes? Take this guy's contraction in the Jonas way. See if the outcome is an invariant. If so, this was a four vector. If we can prove that, then we have really made huge progress today.
What do we take as invariant?
Yeah, that's
So I'm going to go to the bathroom, see if I can get some coffee on the way back.
I do not.
20 hours was late last night, so I need my coffee. I'll be back.
Thank you.
Because it's easy just to calculate the
fucking got lost here. Where the
Minkowski
fuck
line
did we
element
get
and
these
just
numbers
apply
from?
the contracting and
Okay. You understand
What did you say?
Yeah, just adding them in.
Congratulations, you ought to be so
I'm even
polite,
slow.
huh?
Yes.
I'm always
Yes.
polite, you know.
Yes.
And then move all the pieces
So,
to the other
So
side.
just write this one here.
The thing is that for this, it's not so complicated because you had your invariant thing.
Yeah,
Yeah,
you know
he
what
gave
should
us
be
the
invariant.
equation. Yeah.
Let's find the invariant version.
Where is
Minus p squared, but really it's p